ఇందులోనే మాట్లాడతా. మళ్ళీ నువ్వు ఏం తెచ్చుకున్నావు, వేరే తెచ్చుకోలేదు కదా. అది చూస్తే ఇందులోంచి క్లిక్ చేయనా. జూమ్ లింక్ నుంచా? జూమ్ అడగకుండా ఏదో అడుగుతుంది ఎందుకు? Good morning, all of you. అందరూ రా చేసేసాను. ఇప్పుడు ఇక్కడ నుంచి ఇది లాగిన్ అవ్వలేదుగా సిస్టమ్. నా మైల్లోంచి వెళ్ళాలి కదా. మీకు వస్తుంది. ఇప్పుడు ఇది షేర్ అయిపోయిందా? నువ్వు ఇంకా నువ్వు మ్యూట్ చేయాలి కంప్లీట్గా. ఆ వాయిస్ వినపడకూడదు, గుర్తుపెట్టుకుని మాట్లాడేది. నీ దగ్గర వస్తుంది కదా ఇప్పుడు, స్పీకర్ ఆఫ్ చేయి. అర్థమైందా? Good morning, all of you. Just we are waiting for a few more participants to join. We'll start in 2 minutes inauguration program. Morning, all of you. మళ్ళీ నాకెందుకు వస్తుంది? Okay, welcome to all the participants. Welcome to all for 1 week AICTE, ISTE sponsored online faculty development program on Python programming for 5G communications from 14th to 22nd February 2022. Welcome to all, and welcome to our Chief Patron Dr. Mari Lakshman Reddy Garu, Chairman, MLR Group of Institutions. Welcome to Dr. Sri Mari Rajshekar Reddy Garu, Secretary, MLR Group of Institutions. And our convener, Dr. K. Srinivas Rao, Principal, MLR Institute of Technology. Okay, just I will explain the complete schedule of our FDP program. Starts from 14 to 22nd. So the morning session on 14, implementation of wireless cooperative NOMA networks by Dr. Kiran Kumar G, NIT Andhra Pradesh. And afternoon session, the downlink signal processing in 5G system by Dr. Abhay Kumar, IIT Roorkee. And tomorrow morning, basics of Python programming, Dr. L. Pallavi BVRIT. And in every session between the 2 hours, each session carries 2 hours. In between, we are requesting the resource person to give 5 minutes of break. And the well-known, reputed experts and completely on 5G communications. So please utilize these all services. And some sessions on hands-on. So this is an online program, even though you try to listen the session either on laptop or in desktop so that you can practice some sessions hands-on. So tomorrow afternoon, index modulation techniques for 5G communication, Dr. Anuradha, NIT Warangal. And on 16 morning, so daily the morning session will start at the time of 10:30 a.m. and up to 2 hours of session to 12:30. So on 16th morning, 5G advances reconfigurable intelligent surfaces by Dr. VV Mani, NIT Warangal. And in the afternoon session, daily we are starting at 2 to 4 p.m. So the role of edge computing on IoT enabled 5G network, Dr. E. Suresh Babu, NIT Warangal. On 17th morning, 5G technology spectral efficiency perspective, Dr. Rakesh Singhoi, Director UIT RGPV Simhapuri is a complete practical. They are working. It's a industry person working on 5G technologies. So he will deliver more practicals related, practice oriented. And on the 17th evening, post OFDM waveforms for beyond 5G communication systems, Dr. B. Krishna Chaitanya, Mahendra Ekola University. On 18th morning, on Python, data structures in Python programming by Dr. N. Usharani, Vignan University. And in the afternoon, antenna array pattern synthesis for 5G communication, Dr. Gopiram from NIT Warangal. And we have a break on Sunday. Now we are getting this. 19th morning, 5G networks, innovative concepts. Professor Ramamurthy, Mahendra Ekola University. And afternoon, antenna array pattern synthesis for 5G communications by Dr. Gopiram, NIT Warangal. And on 21st morning, Dr. K. Alaya, NIT Warangal on data visualization using Python. And afternoon, 5th generation wireless communication technology by Professor Arun Kumari, BITS Hyderabad. And on 22nd morning, we'll optimize 5G RAN, resolve complex RAN issues in 5G advanced 5G RAN troubleshooting by industrial expert Mr. Y. Malleswar, CTO, Inverse Technologies. So completely practical exposure. They will explain on 5G. And on afternoon on 22nd, we'll conduct a test and we'll take feedback from the participants and we'll conduct a validatory function. And we'll take feedback on every session. So whoever participated, please give your valuable feedback on each session so that the resource persons will feel happy on your feedback. And if anything required, we'll try to modify the session by session. So your feedback is valuable for the session. So I'm requesting all the participants to attend the session on time. So the link, whatever we are given today, the same link you can use to join for every session from 14 to 22nd. So in every session carries a 2 hours of session. In between the 2 hours, we will request the resource person to provide a 5 minutes of break so that you can utilize that break if required anything and join immediately. Today's session is going to start in 5 minutes. Implementation of wireless cooperative Noma networks by Dr. Kiran Kumar Gurrala. He is from NIT, Andhra Pradesh. So now, just a brief introduction about the today's expert. Now I feel privileged to introduce today's speaker, Dr. G. Kiran Kumar. Currently, Dr. G. Kiran Kumar is working as assistant professor and head in the Department of ECE and NIT Tadepalagudam. Dr. Kiran Kumar did his PhD and PG at NIT Roorkela. His specialization particularly in wireless communications. His research interests including cooperative communications in wireless networks, particularly in 5G, and physical layer security, resource allocation, and Shah continuously professional educator with a solid commitment to the academic growth of development, continuously engaged in the organizing of national and international conference, particularly in the 5G communications, and organized so many webinars. So now I'm welcoming Dr. G. Kiran Kumar, sir. Please be wait. Just the sir will start the session. Before moving ahead, I request all the participants kindly mute your mic and camera. And if you have any question during the presentation, feel free to message in the chat box. So please be present continuously throughout the session. So your attendance is noted for each session. So the continuous from 14 to 20 seconds, an average of 80% of attendance is mandatory to get the e-certificate. So please be, we are all the faculty, so we are in the online mode. So don't disturb the classes while the resource person is teaching. So we need your cooperation to success the program. So please wait. In 1 minute, the session is going to start. Welcome to Dr. G. Kiran Kumar, sir. Sir, just now I make a co-host. So, good morning, sir.
Thank you, sir. Good morning, sir. Am I
Kiran
audible,
Kumar,
sir?
sir.
Good morning, sir. Good morning, sir. Thank you, sir. Hello. How are you, sir?
New speaker better.
Am I audible, sir?
So voice is very low, sir. Now it's good.
Sir, good morning, Kiran Kumar, sir.
Good morning, sir. Is my voice audible, sir?
Yes, sir.
Okay. Thank you. Start the session, sir.
Yes, sir. Audible, sir.
Okay, sir.
Welcome,
Shall I
Dr. G.
start?
Kiran Kumar, sir. Kiran Kumar, sir.
Hello. Hello,
Kiran Kumar, sir.
sir.
Kiran Kumar, sir.
Sir, am I audible, sir? I think am I audible, sir, now? Sir, check my voice now. Am I audible to you all?
Yes, sir. Yes, you are audible, sir.
Okay. Shall I start the session, sir?
Yes, please, sir.
Okay, sir. Thank you.
వేరే వాళ్ళు
Is it visible to you all? Is it visible?
Yes, sir, visible. Sir.
Okay, thank you. So
Yes,
good morning,
sir.
one and all. Good morning, one and all. Today we are going to discuss about this implementation of wireless cooperative Noma network. As a part of this, we are going to discuss these things in our session: introduction and what is a cooperative Noma network, what's the meaning of cooperative relaying concept, and what is Noma, what is the need of Noma in next generation wireless networks, especially from 5G onwards, 5G and beyond, what is the need of Noma, and what is Swift technology. If you combine these three, cooperative relaying, Noma, and Swift, how can we propose a new type of system models? What are the possible system models we have? And one of the possibilities is Swift enabled to cooperate to Noma based IoT network. And for that, how to do performance analysis or resource allocation? What are the future challenges we have? So these are the possibilities we'll see in this session. So first we get into the topic of cooperative wireless Noma network. And within that, what is cooperative relaying? Then what is Noma and what is Swift? How the combination of these three will produce a productive system model which can address the problems which are occurring in 4G and which will be a better solution for next generation wireless networks. So these things we will discuss. So now I'm explaining that. I think it is visible. So first we will discuss about the first one, cooperative relaying. One minute. The significance of cooperative relaying, then what is Noma and all we'll discuss. So first we'll discuss about cooperative relaying, then Noma, and then Swift technology. A combination of these three will present as a new system model. Coming to the first one, cooperative relaying. And from 3GPP LTE onwards, that means fourth generation, before fourth generation, third generation mobile onwards. So there is a presence of cooperative relaying. So first of all, what is the need? What is the meaning of cooperative relaying and all? So as we are moving from one generation mobile to another generation mobile, in the evaluation of mobile communications, there is a need of improving the data rates. There is a need of increasing the spectral efficiency. What's the meaning of this spectral efficiency problem and energy efficiency problem? Every generation networks, every generation mobile communication or wireless communication having two challenges every time. One most important is spectral efficiency, because day by day the number of users are increasing, but there is no change in the available spectrum. Spectrum always limited, but the number of users are day by day increasing, and the data rate value is also increasing day by day. So today on an average every user is about to get 1.57 GB or 2 GB per day on an average, 2 to 4 GB data based on the need. If we get into 5G, daily every user may get 13 GB per day. So that means as the day by day increasing, you are moving from one generation of mobile to another generation of mobile. There is a need of increment in data rate. There is a need of increment in number of users, but there is no change in the available spectrum. Spectrum always limited. How to accommodate, how to provide service to many number of users with the limited spectrum. That is the first spectral efficiency problem we have. So that we can call it as a spectral efficiency problem. So within the limited spectrum, how to allocate many number of users within the limited spectrum. So that is the spectral efficiency problem. And coming to energy efficiency, how we can do this task with the limited energy for each node. So let us take a simple example. So previous case, we have let the spectrum like this. A space which is occupied the range of frequencies. The range of frequencies is nothing but spectrum. Let us assume this is a spectrum we have. Previously, 100 members are used to occupy this. So 100 members, 100 subscribers are there to use this available spectrum. Though the number is increased to 1000, but there is no change in the available spectrum. The number of frequencies are same. Now, how to accommodate this time 1000 number of users within the limited spectrum of this? So within the same space, I have now only one stair. I can increase the number of stairs, where each stair occupying 100 number of users. So make a new stair and make a new stair again, and keep on increasing the number of stairs. And I need 10 stairs, where each stair accommodating 100 members, which is equals to 1000. So that means indirectly we are increasing the height of the building, which is nothing but operating frequency. You are increasing the operating frequency from one generation to another generation. That's the example. If you take first generation, second generation mobiles, they are operating at low frequencies. Now, if you see the operating frequency of 4G, approximately 2.73 gigahertz. It is in terms of gigahertz. If you 5G comes into picture, you are moving to visible light communication, much more increment in operating frequency and all. As the frequency increases, we know the wavelength decreases. We are moving upward in the electromagnetic spectrum. Now we are near to the visible light, then we are ultraviolet, X-rays, gamma rays, and so on. So we are moving towards ionized radiation. So as the frequency of radio waves keep on increasing, so we can able to accommodate many number of users. Spectral efficiency problem will be addressed. But other side of this, you are increasing the frequency means you are decreasing the wavelength. If you decrease the wavelength, the signal has the ability to penetrate into your body at any level. Based on its operating frequency, sometimes it becomes as an ionized radiation. It has the ability to break your bone also. If you want to send some information signal, you want to share some data with any one person continuously, not only the free space, our human body also acts as a medium to that radio signal. If a 5G comes into picture, our next generation wireless networks about to come into picture. And real-time usable condition case. If any human being continuously operating a 5G or beyond 5G mobile continuously more than 20 minutes in a day, surely he has impact of that radiation that will be accumulated in our body in some other form. So these are the other side of our existing or upcoming next generation wireless networks. But coming to our topic of cooperative relaying, limited space, limited spectrum, which can be used by many number of users, or limited spectrum, more number of users they are accommodating. So during this process, to increase the data rate, we need multiple antennas. We need multiple antennas that we can call it as MIMO systems generally. Multiple input, multiple output antenna systems. So multiple antennas at the transmitter, multiple antennas at the receiver. Because if you have more number of antennas, more number of signals to be generated, more number of signals to be transmitted. Obviously, we are increasing the data rate because many number of signals are getting multiplexed from that transmitted from the transmitter, they're getting received at the receiver. So because of these multiple antennas, we are getting many other benefits. We can address the spectral efficiency, we can increase the data rate, channel capacity, and we improve the diversity of system also. And indirectly we can say we can provide better reliability of the system. How we can do both the things? So let us assume 2x2 MIMO system. 2 antennas at the transmitter, 2 antennas at the receiver. If you send same signal over 2 different antennas, so now the paths are one signal from this and second signal from this, the copies are same. I'm sending the same signal X over 2 transmitting antennas. So that means we are increasing the diversity. The signal has 2 different ways to reach the destination. At least among these 2, one signal may reach the destination. Suppose if you have only one path and don't have any assurance whether the channel quality is good or bad. So there is no assurance for our signal that will surely reach the destination. But at least here we have 2 different paths. So the diversity order is 2. Because the same signal propagating in 2 different paths, at least one path may reach the destination. So the diversity order will increase if you broadcast the same information signal over different paths or different antennas. Suppose different signals were transmitting. You are with the antenna 1, you are transmitting X1 signal, with the transmitter 2 or a second transmitting antenna, you are sending X2 signal. 2 different signals, X1 and X2. Instead of sending only one signal as 2 copies, you are sending 2 different signals that increase your data rate. Because previously only one signal, 2 copies. Even though the receiver has the ability to receive 2 signals, it is our 2 copies of the same signal. If you considered only about the information signal, information content is only half of, because 2 signals transmitted of the same information, same copy will be received. But instead of sending only one signal, 2 different signals, data rate will be improved. So using MIMO system, we can address this spectral efficiency problem, data rate problem, channel capacity problem. But there's a problem with the MIMO system, because now we are operating at 5G. Now we are calling it as a massive MIMO also, more number. It's a collection of many number of antennas. But there is a difficulty with respect to this massive MIMO system. Physically, if you have multiple antennas at the transmitter, more number of antennas at the transmitter, you keep on increasing the number. The first question, how to provide isolation between these antennas? It is very difficult to overcome the interference created by the signals which are located at the same transmitter. All the antennas should generate different signals and they should be isolated with each other. To overcome the interference created by the antennas which are located in the same transmitter and the same receiver. So establishment of multiple number of antennas at each node is very difficult in a network, and maintenance of these many number of antennas is difficult, and it is not economy also. It's sometimes more complex to do this because we have interference problems. So every time we need to create isolation between the signals which are generated from different multiple antennas at the transmitter. Now there is a feasible solution from 3rd generation onwards. That is nothing but our cooperative relay. Let us assume there is a network. A source node is there. You want to communicate with the destination. You want to send some information. He has only one antenna. Now the direct link is not good. So the path between source and destination, the channel is not good. It is of poor quality. So another node is there. We can call this as a relay or a helper or cooperative agent. So he is also a trans receiver circuit. Every node can act as a trans receiver circuit. So the relay transmitting its own information. At the same time, it is helping the source to send its information to the destination. Because our direct link between source and destination is not good, we are taking the help of another node. So now it will help us to send our information to destination. So through the indirect path, our signal is having the capability to reach the destination. So this is called cooperative node. or relay node. It is also having an antenna. Now see, physically every node having only one antenna. So one antenna, one antenna, one antenna. But we are taking the help of relay node. So we are using this antenna also. Virtually it has now two antennas. One antenna of its own, another antenna of relay. So combinedly it is a MIMO system of 2 by 2. Because two antennas it is having from source point of view, from destination point of view also it is having two antennas. So it is 2 by 2. So the cooperative relaying another name is called cooperative diversity. How it is diversity? We are physically locating different antennas at different locations. It is one kind of space diversity. In space, we are creating the diversity between antennas by locating. It is simply virtual MIMO. It is virtual MIMO. It is not a physical MIMO. Every node physically not having more number of antennas, but every node having single antenna only. But it is creating the benefits of a physical MIMO system by sharing its antenna with other nodes. A simple definition of this virtual MIMO is all single antenna users share their resources like antennas, like bandwidth, like channel, like power, like this kind of resources. So the nodes in a network share their resources to form a virtual MIMO is called cooperative relaying. Is called cooperative relaying or cooperative diversity. The name itself cooperative means there should be a need of sharing. There should be a need of sharing. So now this will address many problems of MIMO system. It is alternative to MIMO system. Suppose I want a massive MIMO network, 100 by 100 number of antennas. It is difficult to provide 100 number of antennas within a single node in a network. Instead of that, every node equipping with finite number of antennas and it is sharing its antennas with other nodes. All the nodes in this network, we have 3 nodes. They are sharing their antennas, their resources. So that's what every node having its own antenna and other 2 antennas. So it has 3. It is taking help from relay, so it is 2. If you keep on increasing the number of relays, if you keep on increasing the number of user elements which are helping to us, automatically we are increasing the size of the MIMO, number of antennas. So this is the solution of or alternative possibility of using a MIMO system, physical MIMO system called as virtual MIMO, called as cooperative diversity. Another name we can call it as cooperative relaying. So this is existing in our literature. So many researchers are applying this cooperative relaying concept from 4th generation or 3.5 generation onwards. So that we can call it as a 3GPP LTE, 3rd generation program peripherals, long-term evaluation. From there onwards, we are including the concept of cooperative relaying in wireless networks. The type of network may be anything. It may be a cellular network. It may be a satellite communication link. It may be underwater. It may be vehicular. It may be device to device. It may be machine to machine. Any kind of network, we have the nodes. The nodes sharing themselves. So they are forming a sharing, common sharing between them. We can call that as cooperative relaying. We can call that as cooperative relaying. So this is the basic explanation about this cooperative communication or cooperative relaying, which is alternative of MIMO system. Now the second one is, what are the basic relaying protocols under this cooperative relaying? It is assume source is there, destination. We are taking help from a relay. So our direct link is not good. That's why we are depending on this. Even though our direct link is good, if you consider 2, one is direct path, another one is indirect path, diversity order getting increased. Now the diversity order is 2 because we have 2 paths. Number 1 path direct path, number 2 path indirect path. Now the question is, how the relay responding to the incoming signal from source? Based on the nature of the relay, how it is responding to the incoming signal from source, can classify the relying protocols. Before coming to this, so there is a standard representation of any wireless communication system in wireless domain. Let us assume from transmitter to receiver, I want to communicate information X. So in between transmitter and receiver, I have a channel, a medium, which is having an impact or channel coefficient of H. Now the signal which is received at the receiver is Y. Now how to relate Y and X is the representation of any communication system. In any wireless communication system, the representation is like this one. How to relate the received signal with the transmitted signal with the help of channel. That's the representation of any communication system. Now I want to relate Y and X. Y is the received signal, X is the transmitted signal. Ideally, I want to make it as equal. If Y is equal to X, it's a perfect transmission. Whatever the signal I have transmitted, that only I received at the receiver. But in between, medium is there. It has some impact. If you observe the same kind of thing from signal processing point of view, now we can visualize this medium as a time variant or invariant system. Now it has having the impulse response of H. Now how can we do it? So H in convolution with X. If you observe this from signal processing point of view, in communication point of view, if you consider the system, the medium as time variant, you have to take convolution. If it is invariant, so even though it is a time dependent or independent, I'm saying it is independent of time. So surely convolution becomes as multiplication, simply multiplication. In ideal case, we can write this as Y is equal to Hx by assuming that the timing invariant nature the channel has, and plus N. Every channel having an impact of noise that will be represented as plus N. So Y is equal to Hx plus N. This is the standard representation of any communication system, any wireless communication system. Y is equals to Hx plus N. Here the assumption is time is invariant in nature of any channel. Then only we can write the convolution as multiplication between these two. Y is equal to Hx plus N, where N is the noise. The special noise we can call it as AWGN, additive white Gaussian noise. And information is X and H is the channel impact. And some important factors relating to this, I'm writing it as plus N. But remember, most importantly, it is ideal in nature. It is not possible in real time because noise is random in nature. It is unwanted signal. The form of the noise may be anything. So noise not always come politely and will be added to the signal like this plus N. So noise may be scaled, noise may be convoluted, noise can disturb the signal in any format because the nature of the noise is random. We don't know how it can be. So, but I'm writing it as plus N. I'm writing it as plus N. So how we can visualize, how we can understand this? Among all the possibilities of noise, minimum impact we will get from noise is the plus. Let us assume the noise impact is 10 dB. If you add 10 dB to the signal, or the noise is scaling, so if you multiply with the 10, so minimum impact you will get from the addition. Among all the possibilities of noise, minimum impact you will get from addition. That's why it is additive in nature, because it is ideal noise. And coming to white, there is a specialty of white color where the other colors don't have that. So white is white wherever it is, because if you take an example of blue color, light blue, thick blue, sky blue, different variations we have. But coming to white, it is white wherever it is. It indicating uniformity, constant power spectral density. In simple meaning, the response of this noise to any signal, whatever may be its operating frequency, the response we are getting from the noise is the same. That means independent of frequency, over the total spectrum of frequency range, the impact from the noise is same. The noise impact is the same. That's why it is white. And coming to Gaussian, So I'm saying it is random in nature. The noise is random in nature. So random signals cannot be determined with instant values. Instant values. Take an example of any class. If you randomly ask the marks of any student, the marks of individual candidate cannot determine the performance of a class because the class performance is random in nature. So we need to take average of the class or standard deviation. So before that, we need to distribute the signal. Any random process should be analyzed with the help of distributions. Observe the behavior of noise for some time over some interval. Observe their movements of the noise. From that we can. So it is possibility we have. There is a possibility we have to determine or to analyze the noise with the distribution only. We have to take some set of values. So for that we are taking distributions. Among all the distributions we have, again Gaussian distribution having a special because it is having symmetry over the origin. It is having symmetry. Even though it is a random nature, we are distributing it. It seems to be systematic. It has a mean of 0 and it is symmetric about the origin and with the variance like this. If you add or if you include all the ideal qualities of the noise, it will become AWGN noise, additive white Gaussian noise, additive white Gaussian noise. So that's why we are representing any system with the help of the channel coefficient H and additive white Gaussian noise N. And depending on the type of channel, coefficients H will be changed. And the minimum possibility we will take as AWGN, but in real time, it will not like that. And one more important factor also, noise not always an enemy to the communication process. This is also an important point we need to remember about, because sometimes noise will help. So let us assume transmitter and receiver, in between I generated information X with a power of 10 dB power and I transmitted through this channel. Let us assume this channel is more faded. The quality of the signal getting degraded. If we keep on increasing the distance between transmitter and receiver, we have the basic principle that the transmitted power of the transmitter signal is decaying exponentially with respect to the distance. It started its journey with a power of 10 dB and it continuously monotonically decreasing its power while reaching the destination receiver. If the distance is very large, it keep on decreasing its signal strength. It almost tends to, let us assume, 1 dB. But the receiver signal or in the receiver circuit, it has some threshold. Minimum threshold it has is 4 dB. All the signals which are having amplitude greater than or equal to 4 dB only will be identified by the receiver circuit. Otherwise, the signal will not be identified by the receiver. The signal will not have any chance to enter into receiver. The signal reached the receiver circuit after a long distance of communication. But its signal strength is very big. It has only 1 dB power. But the minimum threshold we need is 4 dB. Extra 3 dB I want. So in this particular case, 1 dB plus some noise analysis or some noise impact on the signal. Let us assume it is a plus. Now the combination of these two, So 1 dB of signal with some noise quantity, it becomes as some 5 dB. 5 dB. Now the threshold level is 4 dB only. Now our signal has 5 dB. At least our signal having a capability to enter into receiver circuit. Advantage is at least we get a chance to enter into receiver circuit. But the disadvantage is in the receiver circuit, major portion of the incoming signal is from the noise, not from our original information signal. Because in this composite signal of our original information signal with the noise signal, the dominant component is noise. So that's why it is not always an enemy. Sometimes we get a chance to enter into receiver circuit also. Now come back to our analysis again. So what are the basic relaying protocols we have with respect to cooperative communication? So this is the source I considered and the destination and in between the relay. So let us assume here the channel is H, it is between source and destination, so HSD. It is in between source and relay, so it is HSR. It is in between channel, relay and destination, so it HRD. So these are the, let us assume information X is generated from this, and this is the Y. Now we have standard form of any communication system, Y is equal to Hx plus N, Hx plus N. Let us assume the noise in this particular link is NSR, the noise in this is NSD, the noise in this is NRD. Now how this relay will respond to that? Based on that, we can write the mathematical model. So there are two basic relaying protocols. The first relaying protocol, how this relay responding to the incoming signal. Let us assume it is indirect path. It is direct path means less distance only. If it is indirect path, long distance, the signal has to travel long distance. So during this long distance process, the signal strength of X keep on decreasing because long distance communication. The signal becoming weak and weak and weak. It losing its signal strength before reaching the destination D. So what the first job of relay node, how it can help to the source? Blindly it can amplify the signal X and transmit it to the destination. That's the first relaying protocol we have is AF, amplify and forward. Amplify and forward. Amplify and forward relaying protocol. So what the relay will do now, whatever the signal it receives from source, that will be amplified by this R and transmitted to the destination D. Now let us assume the signal received here is YSR. From the basic representation Y is equal to Hx plus N, the channel between source and relay is HSR. The information generated is X. Let us assume the power or energy applied to this signal is under root of PS. Under root of power is energy plus NSR. The noise in this link is NSR. So let us assume this is the signal we received at the relay. What is our AF? Amplify YSR. Amplify the signal received at relay and forward it to destination. Forward it to destination. Now we are making a amplification factor beta into YSR. So we are amplifying by multiplying a factor. We are scaling the received signal. The channel is HRD, the noise is NRD. Now it becomes as YRD. Signal received at a destination D from the relay R. It is the amplification of YSR. Now, what is the simplicity or advantage of AF relaying protocol? It is easy to perform because without analyzing the incoming signal, whatever we receive, blindly amplify that and forward it to destination. The processing of amplify and forward relaying protocol is easy because it's just an amplification of the incoming signal. But there is a limitation of this AF. You are amplifying YSR means you are amplifying the original information content along with the noise content also. So means there is an amplification of noise along with the information signal. It is a limitation. Then when it is a problem, when the performance of AF relaying protocol will not give you better result. Whenever noise is more dominant than signal, information content, then if you amplify again, noise becomes more dominant than the information signal. Then the performance of this communication protocol is very weak. So the advantage of AF relaying protocol is it is simple, just to amplify the incoming signal, forward to the destination. But the limitation is along with the original information transmission, there is amplification of noise also. That's the limitation of this relaying protocol. So this is about AF. The next relaying protocol we have is decode and forward. Decode and forward. So the next protocol is DF. Decode and forward relay. Decode and forward relay. Now the received signal at the relay is the energy, original information signal, the channel is HSR, the noise is NSR. There is no circuitry we have to make completely noise as 0, but we can minimize the impact of noise. Now I want X. This is the decoding. From YSR, detect X. Detect X. Now how we can do this? We can minimize the impact of noise by circuitry. And let us assume it is approximately equal to root of PS X HSR. Let us assume noise is neglected. That's it, approximately. There is a still impact of channel. Multiply with 1 by HSR. Both would cancel out. It is approximately equal to YSR is equals to X. So this is called inverse filter. Inverse filter. Equalizer. Another name is equalizer. So by having noise minimization circuit and equalizer, we can form decode and forward. When this protocol, decode and forward protocol, gives you better result compared to AF. Whenever the relay has better decoding capability, means whenever the relay decodes perfectly, means whenever YSR having a chance to make equal to X, then the performance of this decode and forward relaying is better than AF relaying protocol. The question is when it is possible. When it is possible. When the noise is less dominant than information signal. Another way to say, if the X is more dominant than noise, X is more dominant than noise. Information is more dominant than noise. Then automatically noise will be neglected because it is less in quantity compared to information signal. Automatically it will be neglected. So we can easily detect the original information signal. That is possible. The signal is more, means the signal power is more, the noise power is less. The signal to noise ratio higher value. For high value of SNRs, for higher values of SNR, the decode and forward relaying performance better than AF relaying protocol. So for higher values of signal to noise ratio means signal power is more dominant than noise power. Whenever it happens, signal is more dominant than noise, so noise automatically neglected. We can get the detected version of original signal, that is decode and forward. So these are the basic two relaying protocols we have, AF and DF, and there are some adaptive relaying protocols also. These are fixed, AF and DF, amplify and forward, decode and forward. If you want to do some adaptability, we want to add some adaptability to these two protocols, we can add. And sometimes we can provide a hybrid also. Hybrid AF and DF relaying protocols. You can combine these two, AF and DF. So when the relay has perfect decoding capability, you can go for a DF. When the relay fails to decode it perfectly, then go for AF. You can make a switch condition between these two and you can provide that as a hybrid relaying protocol. Some kind of also the selective relaying protocols, fixed relaying protocols, adaptive relaying protocols. One more type also there, incremental relaying. Incremental relaying. So what this kind of relaying will do? Source, destination, and relay. When the direct link between source and destination is good, no need of relay. When the direct link is not good, then there is a need of relay. Test it. So what in this process of incremental relaying, there are two. One is a testing of direct link. If the direct link is good, this we are not considering the second probability. If the first link fails, then we go for the second. The testing of a first link and verifying whether there is a need of relay or not, this process is called incremental relaying. Incremental relaying. So still we have a chance to propose new kind of relaying schemes. Otherwise, we have a chance to optimize the performance of existing relaying schemes. That also possible. So this is about cooperative relaying. This is about cooperative relaying. Now we'll get into the second one, Noma. Noma. So coming to this Noma, up to 4G we have OFDM, orthogonal frequency division multiple access technique. OFDM. But 5th generation onwards we have Noma. Why there is a need to move from OFDM to Noma? That's the first question we need to answer. So up to 3G, we have OFDM. But there are certain limitations with respect to OFDM. There are many advantages with respect to OFDM. Orthogonal frequency division multiple access technique is one kind of multiplexing technique we have. There is a possibility to combine many signals to form as a single composite signal, multiplexer signal, which can increase the data rate, which can address the spectral efficiency problem in well manner. But we have some difficulties with respect to OFDM. All the carriers, the basic principle of OFDM simple is divide and rule. So we have to satisfy the Shannon theorem. The information signal should not more dominant than the channel capacity. We have the Shannon theorem, R always less than or equal to C. The capacity of the channel. So the rate of information we need to be transmitted over the channel always less than or equal to the capacity of the channel. How to understand this? Let us take a pipe. How much water we can inject into the pipe, that depending on the width of the pipe. The width of the pipe is capacity of the channel. The water level, the content, the level of the water we are introducing is rate of information we are introducing. High data rate signals will not be transmitted through low capacity channels. For that, what you need to do is the rate of information is very high. If you take 4G 1.575 gigahertz or 2 gigahertz signals, at data rate also many number of symbols. So nowadays we are having net browsing, video streaming, and the text data, voice communication, video signal communication, many other things we have. So data rate is surely high. That high data rate signal will not be transmitted through this low capacity channels. For that, what we need to do? Divide this heavy data rate signal into small data rate signals and send each signal with a different carrier. So that's why multi-carrier system is the OFDM. Different carriers we have to take, where each carrier carrying the information of a high data rate signal, a portion of high data rate signal. A high data rate signal divided into low data rate signals, where each low data rate signal carried by one different carrier. Here the condition is all the multiple carriers should be orthogonal to each other. It's the most difficult complex condition we have. So that is, so we need to provide orthogonality between the carriers. We need to provide orthogonality between the carriers. And every time, if you see the block diagram of OFDM signal, the generation of OFDM, the demodulation of OFDM are very complex in nature. And we need to sacrifice some bits as cyclic prefix. We're adding some cyclic prefix. We need to have different multiple carriers, orthogonality between the carriers. Most importantly, we have one limitation of OFDM, that is PAPR, peak to average power ratio, high peak to average power ratio. There's a limitation of OFDM because some carriers having high peaks. Due to that, we are having this limitation. So nonlinearity of high power amplifiers will lead to some distortion. Removing or minimizing this PAPR is difficult in nature. So that's why people are searching for alternative multiple access techniques in next generation wireless networks. So that is possible by the new kind of solution, alternative solution, that is nothing but Noma. So Noma is an alternative solution for OFDM. So in 5G, it is a new kind of multiple access technique. With this technique or with this technology, we can multiplex more number of signals, many number of signals to be combined as a single form of signal. Many to one is conversion is possible. But how we are combining these signals? With what factor they are different, with what factor they are same. So that's the basic principle of Noma. So here, no need of multiple carriers or no need of orthogonality between the carriers is required. The first two advantage with respect to the basic principle of Noma. Suppose I want to multiplex X1 signal and X2 signal. So their operating time and frequency of these two signals may be same. The biggest advantage we have. It is not multiple carrier system, it is single carrier system. Because these two signals are operating on same frequency, they're acting the same time interval. So these two signals are same in time, same in frequency, but they are different with respect to their operating powers. So all the multiplexed signals should be different with each other. In OFDM, we are creating the difference by providing orthogonality. But in Noma, we are providing difference by applying different power levels or with the different operating codes for each signal. If you apply different powers, it is power domain Noma. If you apply different codes, it is code domain Noma. The name itself, you expand the name non-orthogonal multiple access technique. It is alternative for OFDM. In OFDM, we need orthogonality condition, but here no need of orthogonality between the multiple carriers because it is operating on the same carrier, the same in frequency, same in time. So it is non-orthogonal. Multiple access. So it is one kind of multiple access techniques under 5G and beyond. Now people are addressing the same Noma in 6G also because it has the benefits. It is easy to generate. Now the question, how to generate this Noma signal? What is the basic principle? Let us assume here source is there. One near user D1, one far user D2. So I want to send information to these two nodes. Let us assume X1 is the information signal with respect to D1. X2 is the signal with respect to D2. X2 needs to travel long distance because the distance between source and D2 is very long. And coming to distance between source and destination 1 is very small. So here X1 needs to travel a distance of lower level. X2 needs to travel a distance of high level. So long distance I need to travel means more power I need to apply. Let us assume the power coefficient I am applying is A2 for X2, A1 for X1. Now the condition is A2 is greater than A1. A2 is greater than A1. For far user I am applying more power. For near user I am applying less power. It is not only with respect to the distance, with respect to the channel condition also. If the channel condition is good or bad, based on that, we can assign the power. So it is a near user. It is located close to the source. The channel condition is good. So good channel conditions need not more power. So A1 I am applying as low power. And see the link between source and destination. This is channel link between source and destination 2. It is weak channel. So more power is required. More power is required. That's why A2 is greater than A1. If you combine these two, my broadcasted signal, the composite signal now, A1 X1 plus A2 X2. This is the composite signal. This is called Noma signal. Noma signal. We are combining these two. A1 X1 plus A2 X2. If you broadcast this Noma signal to D1 and D2, how these two nodes decoding their own information, selecting their own information, how they are rejecting others. That is the decoding principle of Noma. This is the generation principle of Noma. So the generation principle of Noma signal or basic principle of generating a Noma signal is how many number of signals you want to multiplex, how many number of signals you want to add. For all those signals, find out their proper destinations, how far they are located, how their channel conditions are, if you have perfect CSA. Then based on the location of different nodes, assign different powers to the incoming signals or generating signals and combine them, broadcast them to the different nodes. This is generation of Noma. And now the question is how to demodulate this, how to decode this at the receiver. Now, each node receiving the composite signal because it is broadcasting same signal, composite signal to both. Let us assume A1 X1 plus A2 X2. This is the signal we received. A1 X1 plus A2 X2. This is the signal we received. Now A2 X2. X2 is our required signal. X2 is our required signal. X1 is interference to us. Now the question is, after traveling a long distance, A1 already a low amplitude factor, because A1 is, we are assigning low energy. So the power we have applied to the X1 near user is less power, and for far user only we applied high power. So low power transmitted long distance, automatically it becomes negligible, because A1 already a low power coefficient signal and you transmit it for long distance, it becomes more weak while it reaching the destination D2. It automatically neglected. The remaining component we can select it as A2 X2. So X2 is our required component. So no need to do something at the far user, because at the far user, low amplitude factor based signals automatically neglected. Coming to the near user, the composite signal we have received is A1 X1 plus A2 X2. A2 is more dominant. It is the strong component because A2 is greater than A1. It is easy to identify the strong component. So I identify the signal component, which is A2 X2, but it is not our signal component. Our signal component is X1. So find out the strong component and remove this, subtract this. So A2 X2, both get cancelled out. The left out term is A1 X1. So this is called successive interference cancellation. Successive interference cancellation. So A1 X1 plus A2 X2. X2 is the strong component. It is easy to identify. It is easy to identify. So what we can able to do? So we can subtract this and we can select the remaining component. So X2 is interference to X1 because we are operating at a D1. For respect to D1, our original information is X1 only. All other components except our own information becomes as interference to us. So X2 component is interference to me. So if you subtract this strong component, we can call it as SIC, successive interference cancellation. Successive interference cancellation. So we are subtracting the strong components and we can select the weak component. So the decoding of Noma signal depending on SIC, successive interference cancellation. So at the far user, no need to do SIC. For near user, we need to operate successive interference cancellation. So a source is there, a near user and a far user. This both, I'm applying a composite signal A1 X1 A2 X2 and provided the condition A2 is greater than A1. After traveling a long distance, A1 becomes weak, automatically A2 X2 will be taken out. And coming to the near user, A1 X1 plus A2 X2, it is easy to identify the strong component, but it is interference to X1 because our original signal component is X1. So cancel this and you can take A1 X1. This process of removing the interference component is called SIC, successive interference cancellation. For two users, it is easy to understand the Noma. There are no much difficulties. Suppose it is a multi-user case, because nowadays we are operating on wireless networks where the device connectivity is massive connectivity. More number of devices to be connected. Previously, it is possible to communicate human to human. Now it is possible to communicate any human being with the machine. A machine to machine communication also possible with the artificial intelligence help. So it is a multi-user scenario. So more number of users, more number of signals. Let us assume A1 X1 plus A2 X2 plus so on. There are n number of users A1 Xn. How they are related, how they are different. They are same in time, they are same in frequency, but they are different with respect to their operating powers. So A1 is less than A2 is less than A3, so on is less than AN. It is the far user, this is the near user, and the remaining are intermediate nodes. So AN having the highest power, with respect to AN, all are low power amplified or low power applied signals. So it will be easily separable at the far user, and remaining signal will be neglected. Now, it is very difficult to do successive interference cancellation. Suppose I want A1 component, I need to subtract all other remaining components. N-1 number of components to be subtracted if I want to get only A1 component. So doing successive interference cancellation at the multi-user case is very difficult. So many researchers are still working on this, how to provide perfect successive interference cancellation in the circuitry. So total performance of Noma is depending on a single concept of successive interference cancellation. Because the Noma signal generation is easy, but there is a difficulty with the decoding option in the form of successive interference cancellation. If you are clear about how to separate all the components which are interference to your own signal component, is there any chance of perfectly doing the successive interference cancellation? Then Noma excels everything. So the performance of Noma completely depending on successive interference cancellation, which is the now existing and enhancing multiple access techniques under 5G, and which is useful for future generation wireless networks also. This is the basic about Noma. And coming to what are the challenges we have with respect to Noma. So you can get perfect SIC, and most importantly, if you want to allocate power to Noma, under Noma, suppose I want to assign different power levels to different signals. First, I have to know where the locations of nodes. So node location I want to know. I have to know. Then only we can assign power. So the channel condition, I need to know whether the channel condition is good or bad. Then only I can assign different powers. So we need to have CSI, channel state information. Suppose you don't have any CSI, channel state information, how we can generate a Noma signal? It is a difficulty we have. That's why under imperfect CSI, when we don't have any channel state information, how to estimate it and how to assign different powers to different users, how we can generate a Noma signal is one important research challenge we have. And how to do perfect successive interference cancellation. That is also one important research challenge we have. And how to accommodate this Noma in different system domains. If you apply Noma in cellular network, if you apply Noma in vehicular network, if you apply Noma in underwater communication, if you apply Noma in satellite communication, depending on system capability and flexibility, how we can generate Noma, how to get better performance. This is about the Noma and future challenges. And the last technology we need to discuss, and till now we have discussed about cooperative relaying and Noma. The third one is Swift. Simultaneous wireless information come power transfer. Now the biggest difficulty we have in these days is energy efficiency. Most of the nodes so they are sustainable. So they are getting their energy from some external battery services. We need to provide some energy from outside for the maintenance of the nodes. That is, assume a source and a destination. In between us, we need a relay, a helper, which is always to help us. But coming to its maintenance of the node, how this node can be maintained, the energy requirement of this relay node, how it will get. So we need to feed it with some external power source. If you do energy harvesting, nowadays the most popular word, energy harvesting. Harvest energy for the maintenance of any node from external sources. So no need to have any battery service. You want to overcome this, the lifetime of the node can be enhanced if you do energy harvesting. We have many other energy solutions, renewable energies we have. We can use them for the maintenance of the relay node. So one possibility is we are generating some information signal X, we are transmitting it to relay, and the same signal is to be forwarded by the relay to the destination. Now, for this information signal, we are applying some energy under root of PS. So what the relay can do within the information signal itself, or within the information transmission itself, we are doing energy harvesting. Another way to say, the relay harvests some energy, the relay saves some energy from the information itself. So the information is propagated, X is propagated to R. In the portion of X, some energy saved by the relay for its maintenance, and remaining portion may be transmitted to the destination. Let us assume X, 0.25% or 0.25 of X is saved for R, its maintenance. 0.75X is transmitted to the destination D. And in the D, we have the threshold is 0.5X. Still, it is above that. So it may be received by the destination D. It will be identified and it can process. So this is called SWIFT technology. Simultaneous wireless information come power transfer. Within the information transformation itself, we have power transmission also. A portion of the information signal we have saved for maintenance of the relay node R. So this is simply called as energy harvesting. We are getting harvesting of the energy from the information itself. So this is one possibility we call as SWIFT technology. You can call it as simultaneous wireless information come power transfer. So this is the advantage of this SWIFT technology. So what we will do, so this SWIFT technology can be applied to any next generation wireless network, because every next generation wireless network, including 5G onwards, 5G and beyond, there is a need of energy efficiency problem to address and a spectral efficiency problem. Spectral efficiency well addressed by Noma and new multiplex access techniques, and this energy efficiency problem well addressed by this SWIFT technology. Now the question is, so the relay getting energy from the information itself, but how we are getting? So there are two protocols under this SWIFT technology: time splitting protocol, power splitting protocol. So within the X, you can harvest energy from the information for some time. This is one type of protocol, time switching protocol. And second protocol, some portion of the power of X you can harvest for R. So that is a power switching protocol. So let us assume alpha time of X is harvested for X, remaining portion 1 minus alpha times X to be transmitted to the destination. So the portion of the energy is saved by this R is alpha X. Original signal transmitted is X. Original signal transmitted X. So what is the optimum value of alpha? How much power we need to save for the harvesting of relay without disturbing the transmission from source to destination? And still it has the ability to maintain itself, self-sustainability. We get self-sustainability of every node by saving some energy from information transmission itself is nothing but SWIFT technology. Simultaneous wireless information come power transfer, energy harvesting. So nowadays, some people are working on green communication also. So the meaning of green here, away from radiation. If you want to minimize the impact of radiation, so we have to. So green communication is the solution for many other radiation problems that also you can address. If you combine these three, cooperative relaying, SWIFT technology, and Noma technology, that will become a new type of system model for our case. And most importantly, and coming to the research possibilities under this Swift technology. Dear participants, please mute your mics. Disturbance from the audience side, please mute your mics. Please mute your mics. Okay. So the research possibilities under Swift technology are, you can take any one protocol, whether it may be time switching protocol or power splitting protocol, how much time duration we have to do this harvesting process, or how much portion of the power to be harvested at the relay. So you can optimize the value of alpha, you can optimize the time. Any one protocol you can take, you can optimize with respect to our system model. Those are two research challenges we have under Swift technology. So this is also most important one. And by combining these three, whatever we have discussed till now, cooperative diversity, cooperative relaying, plus Noma, non-orthogonal multiple access technique, plus Swift technology. It is one possibility or one of the possibilities we have for our future research challenge, which can address the problems of next generation wireless network. So cooperative diversity, it is alternative for MIMO system, which is called virtual MIMO. Noma is alternative for OFDM, because we are addressing many problems of OFDM we can overcome by application of Noma if we have perfect SIC, successive interference cancellation. Maintenance of the nodes you will get from harvesting of the energy from the information itself. So simply it is energy harvesting. Energy harvesting. By adding all these advantages, we can propose a new system model. New system model. So we can start our research to address the problems of any wireless network. Now the question is, how we can proceed our research in this new kind of system model. So there are some any kind of system model like this. So I'm writing this source, a relay, and destination. A simple kind of thing. Or in between, I want to add these three. Add these three. Source, relay, Noma. So a relay helping source to transmit its information to different users, D1 and D2, where D1 is near user, D2 is far user. From the information, whatever we are receiving from S, let us assume X, a portion of this one will be harvested at the relay. So this represents our Swift technology. D1 and D2 and decoding with SIC. This represents our Noma. Applying a relay is nothing but cooperative diversity. Now this is a system model for a combination of these three. Cooperative diversity plus Noma plus Swift technology. This is one kind of system model. Now, how we can proceed our research within the system model? What are the steps we have? So this is one kind of system model, and we need to do mathematical modeling of this system model first of all. Write the expressions for received signal at every node. YD1, YD2. It is YSR. So we have channel HSR. This is HRD2. This is HRD1. Now write the expressions for every signal, received signal, that is nothing but a mathematical modeling of the system model. So what are the steps we have, and what is the possibility to continue our research to make it as a big research amount of a PhD level or PG level? First, we need to do performance analysis. We need to do performance analysis. So take any one performance metric, that may be a similar rate, bit error rate, channel capacity, throughput analysis, outage probability, intercept probability. Take any one performance metric, study about that. Suppose I want to consider bit error rate or symbol error rate. The original signal I transmitted is X. It is a collection of bits, 100 bits. The received signal is YD1 and YD2. Compare YD1 with the X, compare YD2 with X. With how many number of bits I have in error position divided by total number of bits transmitted will give you symbol error rate. And we want to calculate the channel capacity. So Shannon capacity we can do. It is W of log of 1 plus signal to noise ratio. So there is a need to calculate link SNR, effective SNR at the destination. Effective SNR at the destination. How we are evaluating the SNR, based on that we can get the capacity. SNR calculation also we can do. How we can get SNR of each link. SNR of each link. But I assume it is a link we have from source to relay. The channel is HSR. The information signal is X. The energy applied is S. And this noise we have in this link is NSNR. Signal to noise ratio, which is represented by gamma. We can call it a signal to noise ratio. Signal power is square of the amplitude. Amplitude is under root of PS. Square of this is PS by noise variance is nothing but noise power, noise variance, and the gain of the channel. The channel coefficient is H, square of the amplitude is the gain of the channel, HSR whole square. So this is called SNR, SNR of any link. Now, I want to improve the capacity. Means by changing the values or affecting parameters, we can improve the SNR. SNR can be improved by improving the power, minimizing the noise, or by improving the channel quality. Any one of these three. Any one of these three. So by allocating different powers, by allocating equal power to all the nodes will not improve the performance. Selectively, if you apply power, if the channel coefficient is not good, apply more power. If the channel coefficient is good, apply low power. Then automatically gamma will be updated. Better gamma will give you better signal to noise ratio. Signal to noise ratio will improve capacity in better way. So like this, we need to study how the channel capacity, how the outage probability, how the symbol error rate. If you want to study about outage probability, so how much probability is there if you calculate SNR, it falls below the threshold value. It falls below the threshold value. If gamma falls below the threshold value, it is not identified by the receiver circuit. It will went in outage. The total signal transmission in outage, no use, completely waste. When there is no outage, whenever gamma greater than gamma threshold, our effective SNR of the system is greater than the threshold, we have a chance to enter into receiver circuit, then our signal will not be in outage. So calculating the probability when the signal transmission becomes waste, when the signal becomes poor, not to meet the threshold, that is outage probability. This also we can calculate. By doing all this, we can do the first step of our research, that is performance analysis. We can complete our performance analysis. Performance analysis. Second thing is define our problem. Define problem. What is our problem? So next generation wireless networks having a problem of increased data rate. I want high data rate. So you can increase the data rate, you can increase the capacity, you can increase the throughput. That is our problem. Maximize channel capacity. This is our constraint or a problem we have under some constraints. How much power we have under different power constraints we have, under channel constraints we have. It may be individual constraint, it may be total constraint. So define our problem. That may be maximizing throughput, maximizing the capacity, minimizing the error, minimizing the outage probability. This is our definition of problem. And the third one is to solve this defined problem. Solve this defined problem with the help of nowadays artificial intelligence help they are taking. So AI, that may be evaluational algorithms, soft computing algorithms, neural networks, machine learning algorithms, fuzzy, neurofuzzy, any kind of thing. It's a set of many things. So we have a help from artificial intelligence. Many of the researchers now are hunting for machine learning algorithms. So you can apply some machine learning algorithms to solve this defined problem. We can propose a better solution. Substitute the better solution in the system and show the performance improvement. Show the performance improvement. So compare with the existing techniques. So compare your proposed algorithms result with the existing ones. Up to this is common. So before doing this we need to create a new system model, which is not in the literature. The combination of new things, like we have proposed Swift technology with the help of Noma, with the help of Cooperative Reliance, propose a new kind of system model. For the new proposed system model, do the performance analysis, then define our own problem. Then with the help of artificial intelligence and convex optimization, strong mathematical solution we have for the problems. Because every problem is a mathematical problem we have in our communications. Solve that using mathematics itself with the help of convex optimization. It is not possible to solve it because it is not differentiable. Then you take the help from artificial intelligence, solve it. And compare our results with the existing scheme. Up to this 4 is a common to all generalized procedure. What makes you to the difference with others? How your work is different? So real-time implementation, experimental validation. So how we can do that? We can create a virtual platform, convert all our algorithms which you have implemented, whether in Python mode or MATLAB environment, do FPGA design, get the hardware implementation of your algorithm. FPGA conversion of your simulation codes, whether they are in MATLAB environment or Python programming mode. So convert them into VHDL. So then this VHDL converted real-time implementation of these algorithms will give you real-time validation of your algorithms. So you can create a test bed and you can commercialize it. All the FPGA designed algorithms will be taken by any industry, because nowadays all cellular networks or many other electronic institutions or industries, they are funding of these FPGA design based algorithms. Many of the researchers, they are completing the mathematical modeling, they are doing the synthesis study, but very less number from India also, they are doing an FPGA design of our algorithms. After doing Python programming or MATLAB programming of your algorithms, convert them into FPGA design. That gives you really an important enhanced version of your research that will be surely attracted by the industries, and you can commercialize your work. So there is a possibility of doing FPGA design. So these are the possibilities of the research challenges. Now we'll get into simple explanation of all these things, whatever we have discussed till now. Cooperative Reliance, Noma, Swift, their basic principles and their operating protocols and their research challenges, and how to create a new system model, how to address a new system model in terms of 5 steps: performance analysis, defining a problem, address the problem, finding out the solution, comparing our solution methods with the existing ones, and after all, whatever the algorithms we have proposed, that may be a resource allocation or performance analysis, how to do those things in real-time environment as experimental validation with the help of this FPGA design. So this gives you the complete picture. These things we will see with the help of a PPT. Now we'll see the slides. What are the slides we have? Is it visible? I think so, visible. Now see, is it visible all? Is it visible to you all?
Yes, sir.
Yes, sir.
Now, just to see the possibilities we have discussed till now. I think cooperative wireless network is clear to you all. So what are the nodes we have? Source, destination, and the number of relays. And we can have a chance to propose new relaying schemes, how to select more number of relays, relay selection, and the usage of relay, and even sometimes nowadays, the capability of the relay, whether it is operating in half duplex mode, full duplex mode, two-way communication relay, and differential mode of relay. So based on the flexibility with the relay also, we can differentiate the cooperative Noma network. And coming to Noma, non-orthogonal multiple access technique, which is the alternative of OFDM. The basic principle, all the signals to be multiplexed are same in time, same in frequency. They are different with respect to their powers or with respect to their codes. Swifty technology, energy harvesting, the combination of these three. First, we will see in Noma. What is Noma? I think we already addressed. Why Noma? We already addressed basic relaying schemes, AF and DF, incremental, diversity combining strategies. All the signals you are reaching the destination, you need to combine multiple copies of the signals at the receiver. How to combine multiple copies at the destination, either from the direct link or from the indirect link. So those are called diversity combining schemes, selection combining, equal gain combining, maximal ratio combining. These are we have the possibilities, future directions. Now see the basic principle of Noma. Let us take a downlink. So base station is broadcasting information to user 2 is far user, user 1 is a near user. At the far user, no need to do successive interference cancellation. For near user only, there is a need of applying successive interference cancellation. Subtracting the user 2 signal, because user 2 having more power, it is easy to identify the strong signal component that is interference to us. So we can directly remove that, subtracting that, and we can decode user 1 signal. And see how these two signals, Noma signal is, they are same in time and frequency. They are operating same frequency. They are operating with the same time duration. So that's why they are, see the levels on x-axis is the same for both user 1 and user 2. But if you observe on y-axis, user 1 with yellow color having less amount of power, user 2 with the green color having high amount of power, because user 2 is far user, user 1 is near user. It is an example of Noma downlink case for user, number of users are 2 only here. It is easy to operate a 2-user based Noma, but we have some difficulties with multi-user case. If we keep on increasing the number of users, how to allocate the power is purely depending on knowing the channel conditions and the location of nodes. And one more important thing in real-time cellular network case, the location of the users not fixed all the time. Every time they are changing the location, because as a mobile unit, it has the capability of mobility. It can able to move anywhere in a place, sometimes towards the base station, sometimes away from the base station. So we have Doppler shift also. So depending on location of the user with respect to the base station, sometimes the operating frequency will increase or decrease. There is a change in the operating frequency also. How to deal with these different signals, different locations, adaptively they are changing their locations. For those kind of situations, how to allocate power is a real-time research challenge we have. We can address that problem also by addressing Doppler shift problem. So this is also an example. If we consider multi-domain Noma, multiple number of users are there, lower link, uplink. You can create any one case, you can get the Noma, any possibility. Now, basic Reliance schemes we have AF and DF. In AF case, whatever the signal we receive at the relay, that blindly amplified. We know the advantage, it is simple to implement, but the limitation of this AM, along with the signal, there is a noise amplification also there. This is the limitation we have, noise amplification along the signal. But coming to decode and forward, we need to decode it, but when the performance is good, it is good in the high SNR region only. Where the signal component is more dominant than the noise component, then the noise will be automatically neglected. We have a chance to decode our signal perfectly. And coming to this, so we provided some literature survey also. Those are interested to start the research, so they can use this also. Some literature till now, what happened in respect to Noma and all. So this is a one kind of Noma network with multiple relays. So see one source, multiple number of relays, D1 and D2. So all the parameters are defined. So this is one type of solution and all. This is another system model, cooperative network with the diversity combining strategies. And new kind of system model, what we propose. So Swift Noma enabled IoT relay network. Nowadays, most of the things they are relating with respect to IoT domain. So that's why I'm taking an example of IoT. So here the IoT, the relay node itself, an IoT node. And it may be any kind of thing. It may be a drone, it may be a mobile unit, it may be a vehicular, it may be a device also. So let us assume I take an example of a smart agriculture, smart radio, smart something. So we need to add some artificial intelligence to the network. So we keep sensors in an agriculture field, we send some information, that information, whatever we collected from that particular agriculture land to be transmitted to the destination and to be updated in the cloud itself. So with the help of IoT nodes, those IoT nodes, they are maintaining themselves from the energy harvesting that they are getting information from base station itself. So there are two arrows, one with the green color, one with yellow color. Green is energy harvesting, yellow is information transmission. So Swift technology. So some users are near, some users are far. So the signal transmission to these two kind of category of users is a Noma. And in between the helper nodes, we have relay nodes. That is nothing but our cooperative communication. So it is a combination of these three. So Noma, Swift, and cooperative. You can need to update. So this kind of system models are not in literature. You can take it as a reference and you can do some modifications. If you want to add something, you can add. If you want to remove something, you can remove. But take it as a reference. Now, these are the steps we already discussed. System model we need to frame. Performance analysis we have to do. Performance analysis may be with respect to any performance metric, that may be with respect to symbol error rate, channel capacity, outage probability, intercept, throughput, some throughput, anyone. So define our own problem, optimize it. Here the optimization, you can take the help of anyone and compare with the existing schemes. Experimental validation is the last step, is the most important factor which differentiate you from others. Experimental FPGA design of all the communication algorithms we have proposed. The real-time validation is not there in India, especially in communication domain, where the signal processing, image processing nowadays increasing their level of FPGA design. When coming to communication, still it is under low level only. If you want to propose, you can propose. Whatever may be the Python programming or MATLAB programming you have, just convert into FPGA design mode. Convert into VHDL mode. That gives you immense enhancement to your research. You get more publications and you can commercialize it as a patent, and you can give your implementations, VHDL implementations to any industry to develop a test bed, surely. And see what are the possibilities we have considered till now. So they are at a basic level only. You can test in different channel conditions. That may be a flat fading, frequency selective fading. You can enhance these things and you'll get the performance analysis also. And with respect to all these three, Swift, Noma, and cooperative relaying, still more limitations are there you need to address. And literature also provided with the slides. Those who are interested, go through the literature and see the possibilities, whatever we have to change. Then you can implement our own system model, address that. So these are some references we have related to some recent literature where the problem actually started, and basic about these three we have implemented. Okay, so these things we have. And any doubts if you have, we can ask. Otherwise, we will discuss some other research possibilities we have to implement, that we will discuss in last 10 minutes. After our doubts in this session, I will refer you some future challenges where you can progress your work. Till now, if you have any doubt, you please ask.
Can you please tell me what is incremental relay?
Incremental relaying is basic relaying protocols only, AF and DF, but with the testing. When we need a relaying, so when the direct link between source and destination is not good, then only we need relay. So we keep a switching condition. First test the direct link. If the direct link fails, then go for the relay. And in the relaying case, you can use either AF or DF. But before going to AF and DF, test the direct link. So that you can have a probability condition. If the probability of the direct link is greater than some threshold level, use the direct link only. If the probability of the direct link is not greater than some threshold, automatically use the relay. If you combine these two, provide a switching condition, that is incremental relaying.
Okay. That means if you before going to AF or DF, we need to test with the incremental relay. That is incremental relay.
That is incremental. That is incremental relaying means actually direct link. If you increase that, that will be act as a relay. That will be neither AF or DF. Before going to increment the layer to one to another, first test the direct link. The
Okay.
direct link
Thank you.
SNR is less than or equal to threshold. It is not good. So we need to go for relay. That's the test we need to.
Okay.
Yes, ma'am.
Okay, sir. Thank you. Thank you.
Thank you, ma'am. Any other doubts?
Dear participants, if you have any query, please ask. So no one is asking. Thank you, sir. Thank you so much, sir. The session was very enlightening. It helps in developing new insights into the domain of 5G technology. Surely our participants have learnt valuable things, and after this FTP, they will be able to explain and explore 5G concepts in a better way. Thank you very much, sir. Thank you.
Thank you, sir. Thank you very much. Thank you all.
All the participants are requested to join the next session sharply by 2 p.m. Now go for lunch. Thank you.
Thank you.
Hello. Hello, Fardu sir. Hello.
హలో వినబడుతుంది. Before moving ahead, I request all the participants kindly mute your mic and feel free to write in chat box your active participation without. So I want to introduce afternoon session resource person, Dr. Rabbi Kumar Shah. Dr. Rabbi Kumar Shah received the BTech degree in ECE from the JP Institute of Engineering and Technology, Guna in 2010, and the PhD degree with the Department of Electrical Engineering, IIT Kanpur in 2017. After PhD, Dr. Rabbi has worked at Samsung R&D Institute, Bangalore as a senior lead engineer from January 2018 to September 2019, where he primarily worked for 3GPP, Reliance, REL 14 feature developments. Later, he worked at Redisys India Private Limited, Bangalore as a lead software architect and was involved in the PUS CH algorithm development for 5G base stations. Currently, he serves as an assistant professor in the Department of ECE, IIT Roorkee. His research interests are in realizing massive MIMO systems for next generation wireless technologies and in the applications of deep learning for wireless communication systems. He is a recipient of the SEDGE Startup Research Grant, DST Inspire Faculty Program, TCS Research Fellowship, and the Vice Chancellor's Gold Medal for outstanding performance in his bachelor's degree. He also received the Samsung Citizen Award for his contribution to 3GPP REL 14 features. Without taking much time, I would like to invite Dr. Rabbi Kumar Shah to start this session. You can start, sir. Over to you, sir. Thank you. Sir,
Yeah.
unmute, sir.
Sorry. Yeah. Is my screen visible?
Sir, it is visible, sir.
Yeah, thank you. And thank you for the kind introduction. So shall I begin? Shall I begin?
Start, sir.
Okay. So good afternoon, everyone. So today we are going to talk about the downlink signal processing in 5G system. And before proceeding, let me introduce myself. I am currently affiliated with IIT Roorkee and I am working here as an assistant professor. I have 10 plus years of experience in the field of 5G system, in particular massive MIMO system. I have worked at like leading development 5G development centers like Samsung and Redisys. I have 20 plus IEEE journal and conferences and 10 plus patents on the related technologies. So let me move with the outline of the talk. So we will start with a physical downlink shared channel, and we will understand what is the purpose of this channel in 5G system. Then we will talk about the signal flow in physical downlink shared channel. Then we will talk about two channel processing. That is, first one is the transport channel processing, which involves CRC attachment, segmentation, Ldpc coding, and rate matching. Then we will talk about physical channel processing that involves scrambling, modulation, layer mapping, antenna port, etc. And then we will talk about a MATLAB model to replicate this entire channel. And finally, we will conclude this talk. So before proceeding, let me introduce the differences. So if you want to go through all these slides, so the major point source of reference is that the 3GPP standard. 3GPP stands for Third Generation Partnership Project, and it has it started with the 3G evolution, and then the same group has continued development of 4G and then 5G. So the standard numbers are 38.211, 212, 213, and 214. So you can refer that. As a credit, I have taken few pictures from this website, and if you want to go go through all these slides, you will able to find the content at this website also. So let me start. So what is a physical downlink shared channel? So this is the channel used for downlink data transmission. So whatever information, the actual information that we are transmitting in 5G, this is the channel responsible for that in downlink direction. Along with data, it is also used for transmission of paging information. Paging informations are like sometimes base station broadcast some information, some messages to all the users. So those kind of information comes under the paging information. Random access response. Whenever UE wants to, and a user wants to access the base station grants a response message. That is random access response message. That also can be conveyed through this channel. And there are some system information that are useful to decode the data that also is conveyed through this downlink shared channel. So this entire TDSCS signal flow is something like this. It is divided into two parts. The first part is transport channel processing. So here, if you see, the block number 1 to 6. So this block number 1 to 6 are responsible for transport channel processing. And then we have block number 7 to 12 that is responsible for physical channel processing. After block 12, we PDSCA channel uses a CP OFDM, that is cyclic prefix based OFDM based transmission to the medium. So we will now talk about all these blocks one by one in detail. So we will start with transport channel processing and with the first block, that is CRC attachment. CRC stands for cyclic redundancy check attachment. It is what we do, we add some parity bits to the actual message bits. The idea to add some parity bits is to facilitate a block error detection at the user side. If a user do a CRC decoding and the CRC decoding fails, it triggers a negative acknowledgement. Negative acknowledgement means the user will initiate a negative acknowledgement that it is not able to decode the packet correctly, and it will ask the base station to initiate the retransmission procedure. So it's a very important part of the entire block, and it is used primarily for detecting the error, whether there is some error. You have done entire decoding at the receiver side. Based on this CRC, you will be able to know whether your CRC has been decoded correctly, like your packet has been decoded correctly or not. In case it is not decoded correctly, the user will send a NAC, that is negative acknowledgement, and base station will initiate a retransmission process. It will retransmit the same packet again. So the procedure is something like this, that if your transport block, that is the bit sequence A0 to A capital A minus 1, that is the size of this input bits are capital A, is encoded as a block of size A plus L. So we add L parity bits so that overall size becomes capital B. So let's assume you have some input bit sequence, which is A0 to A capital A minus 1. So the first thing we do, we check whether what is this capital A, what is this size of this capital A, whether this is less than a number defined in the standard, that is 3824. If this number is less than this, what we do, if the answer of this, if this number is less than this, what we do, we add a 16-bit CRC. So 16-bit CRC means we add a 16-bit number at the very end of this sequence. And these 16 bits are generated using this generator polynomial defined by D16, D12 plus D5 plus 1. In case your block size is greater than 3824, what we do? We add a 24-bit CRC. Means there are 24 bits are added at the end. You can see here P0, P1, P2, P23 are the parity bits that we have added into the bits A0 to A capital A minus 1. And how we calculate these 24 bits? Using the generator polynomial defined by D24 plus D23 plus D18 plus D17, D14, D11, 10, 7, 6, 5, 3, 1, and plus 1. So this is the entire procedure to add the CRC into a bit. So this is the very first thing we do at the transmitter. We have a bit sequence. We added either 16-bit CRC or a 24-bit CRC, depending upon the size of the packet. So let me explain you how we add this CRC, because this numbers looks like very complicated, like there are 24, it's a very long sequence. So what I have considered, so this is like way. So we call this sequence as BI, just for reference. We are calling this sequence as, now instead of A0 and P1, we are calling this as a B0 to B capital B, and this B is A plus L. And this is just a mathematical representation of that. So the first question that we arise is how we will compute this P0, P1, P2, P23 or P15, whether depend. So I have considered a very simple example. So let's encode the message. We have a message 11011. This is the message, and we consider a third-degree generator polynomial. So here, whatever we are doing, it's a small example for third-degree generator polynomial. Same you can extend for 16-bit generator polynomial or 24-bit generator polynomial. So what we do at the first thing, from this generator polynomial, we create a bit sequence. So here you can see this divisor is generated by this sequence. So here if you see D3, so you can write this as a 1 times D3, 0 times D2, plus 1 times D plus 1. So 1, 0, 1, 1. So that is the sequence you can see here. And then what we do in the message sequence, this is 1101, we added 3 zeros. So whatever the length here, we will add L minus 1 zeros here. The first thing we do. And now we will start doing dividing. So the first, what we do, we will take 1 times of this. So 1, and we have 1, 0, 1, 1. Now we will do XOR operation here. So we will do XOR operation. So what we will get? You will get 1 plus 1. That is the first MSB. 1 plus 1 will be 0. And other bits will be, you can have 1, 0 as 1, 0, 1 as again 1, 1, 1 will be 0. And the last bit we have again taken from the actual sequence, that is message bit 1. Again, what we will do, we will again, you can see this, the first bit MSB is 1. We can take again 1 multiply by 1, and then we can again multiply. So we have 1, 0, 1, 1. Now again, you will do an XOR operation. After XOR, this first bit will be 1 plus 1. So again, we are doing XOR, and 1 plus 1 will become 0. Then 1, 0 will become 1. 0 plus 1 will become 1. And this 0 we have taken from this extended message bits. Now we have 1, 1, 0. Again, we will multiply by like 1. 1 times of 1, 0, 1, 1 will be 1, 0, 1, 1. We will do an XOR. So we will keep on continuing this procedure. So what you will do, you will get 1 plus 0 as 1, 0 plus 1 as 1, 0 plus 1 as 1, and again 0. So this will be your second bits in the extended part. Then again, you will have 1 times of this. You will get this sequence. We will get 1, 0, 1. And again, we will take the third bit from this extended part. And we will have 1, 0, 1, 0. So again, we will have 1 times. We will get 1, 0, 1, 0. Now, if you add, what you will get? 1 plus 1, first bit, MSB, 0. 0 plus 0 will be 0. 1 plus 1 again 0, but last term 0 plus 1 is 1. So you will have 0, 0, 1, these 3 bits. So these 3 bits are actually your CRC bits now. So we will pad these 3 bits into the actual message bits. So these are our CRC bit. So our actual message bit was 11011. We have padded earlier all like 30. Instead of these 30, we will replace them with 001. So this is our encoded bits after CRC attachment. So this is a very simple procedure, not very difficult. The only thing is that 5G has this generator polynomial is very large. So while so it's not possible to do it on pen and paper because you need a very long sequence. So so you have to write basically a MATLAB code or some kind of C code or C++ code, any code you have to write, and then you can do all those procedure. But the procedure will be remain same as it is. Now let me ask one question here. So this we have talked about encoding, and even in the entire talk we will only talk about the transmitter side. But at the same time, we should also think about how the receiver will work. So in this case, how receiver will work, you will transmit this encoded bits, right? Probably while transmitting, there are 2 possibilities. You will exactly receive the same sequence, or there might be some corruption in some bits. These are the 2 possibilities. So what you have to do at the receiver side, you have to again perform a similar operation. In case your CRC, you get all zeros here, that means that you have decoded it correctly. Whatever packet, your message bits are correctly, you have decoded it correctly. In case you are like you are getting some non-zero value, it means there is some problem in your actual data. So you will send a negative acknowledgement and ask for a retransmission from base station side. So this is the very first module of that entire chain. Let me move with the second module. Second module is basically about Ldpc graph selection. So CRC is basically responsible for error detection, but it cannot do an error correction. Error correction happens because of the Ldpc code. And the second block asks for how you choose one base graph. What is a base graph? We will come to that part later. So the idea is that depending upon the TB size and the rate you want to transmit, a base graph is selected. We will talk about this base graph in much details once we will cover the block 4, that is Ldpc channel coding. Here we are just picking one base graph. The selected base graph we will use for Ldpc encoding. The procedure is something like that. You have 2 inputs now here, A and R. A was your length of the message bit, actual message bit, the block size. R is the rate by which you want to transmit. So if your A, the transport block size, is less than 292 bits, or your rate is less than 1/4, that is 0.25. In these 2 cases, you will choose a base graph 2. This base graph 2 will be used for encoding purpose in Ldpc. If your answer is no, you will check whether your block size A, I think I have made a typo here. This number should be something 3824. I need to check that. So if this condition fails, you will go and check next condition, that is whether your block size is less than this 3000 something, some number, and your rate is less than 0.67, that is 2/3. If your rate is less than 2/3, in that case also you will choose. If the answer is yes, you will again choose base graph 2. If your answer is no to this question, then you will choose base graph 1. So 2 cases are there for base graph 1. 1 case is there for base graph 1. But if you divide this into a region, like if I plot, let's say here, I have plotted here regions. So in this x-axis, you can see transport block size, that is your A. And in the y-axis, you can see code rate, which is your R. So if I simply draw a line, so these are the, like, you can have 9 regions here, you can see. So if the first condition, if A is less than 292 and R is, so this is the region. This region is this. So in that case, you will choose base graph 2. or see, this is OR. So like what I have highlighted is AND. So basically you have to highlight this entire region, because in this entire region, your rate is less than 1/4. And in this region, your block size is less than 292 bits. So this complete region will be your base graph 2. Second case is this. So this region, if you see this region, is your A is less than 3824. And here, note here, there is an AND here. And your rate is also less than this 2/3. So this region, also you will pick base graph 2. So this entire blue region is your base graph 2. And anything which goes outside this will be your base graph 1. So there are two base graphs. We will use this for Ldpc encoding. So this is the, like we have done base graph selection. Third thing is it's very interesting that we further do a code block level segmentation. Like we have an entire packet. We divide this entire packet into multiple smaller packets. So why we do this? So since you have selected your base graph, so base graph basically we do like at this point I can say that it will be used for a matrix and kind of a vector multiplication. Vector will be your entire bit sequence, and matrix will be your kind of parity check matrix. You will multiply that sequence. So what happens? Your transport block size, which is like A, and we have added L parity bits, that may not be necessarily matching with this base graph dimensions. So we have to do segmentations. If that size is bigger, we have to divide into smaller parts so that we can match with the base graph dimension. So for that, we have to divide the entire sequence into multiple smaller parts. And so that is the first thing. Further, at each like segmented part, we add additional 24-bit CRC. Now this part was new and like it was not done like even in the previous generations of like 4G systems. And why we do this? So like if you see that that transport block CRC, what happens? If that fails, you have to repeat entire packet. But because of this code block level CRC, you can have only, you know that, okay, you have like, let me show you in the one diagram here first. So this was your transport block, right? We have added an L bit CRC. So this was having length L, this becomes A plus L. Now what we are doing, probably your base graph having some dimension, let's say it is having 10 plus 10, and this size is maybe 20. So what you have to do, you have to divide into 2 halves. Then only you can do an encoding procedure. So for that, we are dividing. Now, once we have divided, we have added a 24-bit CRC at each code block. You can see here, at each code block, we are adding a 24-bit CRC. Now, what benefits we are getting by adding this CRC? So assume that this CRC fails. What happens? You have to ask for retransmission of entire transport block, which having, like we have seen, that size was 3824. It can be above, it can be lower than that also. So the size is huge and you have to retransmit so many bits. But if you have divided and you have just CRC and you know that this CRC got passed, this passed, and this only got fails. So you can only ask for retransmission of this particular code block, rather asking a retransmission of the entire transport block. So what it makes your system more efficient. Your overhead on the system will go down. You no need to repeat the same packet again and again, the entire packet. You can repeat only, let's say, code block number 2, and you are good to go. So what is the procedure? Let me now talk about the procedure, how we do this. So the first thing we do that, there is a typo here. This should be code block. So we calculate how many number of code blocks will be. So you have a transport block, how many segment we have to do. So as an input, we consider B and KCB. B is your TB size after CRC, that is your A plus L. So B was A plus L. KCB is maximum code block size. Like what should be the maximum code block size? It is defined by KCB, and this number is 8448 for base graph 1 and 3840 for base graph 2. So now we check whether your B is less than this number or greater than this number. So first thing we'll do, if your B, the entire size is less than this number. So basically, if your answer is yes, you no need to do any segmentation. Your size is itself lower than that. So your number of code block, C defines the number of code block, will be 1, and L, that the parity bits you will add, because the size itself you add and you have not done any segmentation, you won't add any parity to that, CRC to that. So capital L will be 0, and B dash, that is your size of message bits after segmentation, will remain same because you have not done anything. So this case, C is your number of code blocks, L is CRC at code block level. So basically we have not done any code block segmentation and do not add any CRC. So this is the case, a very simple case, but in general, this number will be higher. B will be higher than this KCB. So whenever the answer will be no, we have to do segmentation. So the segmentation is something like this. What we do, we divide B was the total number of bits, and KCB minus L. KCB was this value. So we remove 24 bits from here because we have to add 24 bits to make it align. So we divide that number. So you can imagine that if your B is, let's say, 10,000, what you will do? You will first do 10,000. And if you are a base graph 2, what you do? 3,840 minus 24. You will divide, and this number probably will be the seal. We will take the seal. So you need actually 3 segment of, you have to do 3 segmentations of this 10,000 bits, right? And your B dash, because every segment you will now again add some 24 bits additional. So that will be C times L. So your total bits will become B plus 24 times 3, something like that. So that will be your total bit size. So this is the first thing we do. Second step, so B dash is your TB size after you have added TB transport blocks level CRC and also code block level CRC. So both the CRCs are accommodated in this B dash. So at the second step, we calculate number of bits in each code block. Now we find how many code block will be there, 3. So we decided, let's say 3. Now we have to find how many number of bits will be there in each code block. So that will be defined by K dash equals to B dash divided by C. You just take this ratio because we have taken care while assigning these values, we have taken care this number will be a multiple of that. So if you simply divide, you will get the number of bits in each code block. And probably this number will be like either one of those number 3840 or the other number 8448. So C is the number of code blocks. B dash is the TB size after transport block level CRC and C code block level CRC. K dash is the number of bits in each code blocks. Okay. Now, as a step third, we have to calculate number of bits for matching the Ldpc base graph size. So what we do, so like this we have calculated based on those numbers. Now we have to match basically with the Ldpc base graph. So that we have not done. So that part is something like it is 22 times ZC if you are taking base graph 1 and 10 times ZC if you are taking base graph 2. So what we do, so ZC is an expansion factor we will cover once we will discuss Ldpc encoding. So this 22 times ZC, we will find the K, and K minus K dash, if this value is, let's say some value is pending, so that many filler bits we will add. So we will add some filler bits, and so finally, so now we know everything like segmentation, CRC. So now we will do segmentation and CRC attachment. This is the step 4. So we know how many code block will be there. We know what would be the number of bits in each code block, that is C and K dash. We know what is our actual like transport block after CRC, that is B0 to B capital B minus 1. We know how the value of L, that is 24, we have to add. And we are initializing one variable, that is R, which is for each code block. Like R will range from 0 to C minus 1. It will range from 0 to C minus 1. C is your number of code blocks. So every code block, we will repeat this process. Okay, so this all I have written at the top, you can read. So first thing we do, we initialize, we set an index I and k with 0, and we proceed. First thing we do, we will simply assign bi to crk. So you have, so if you have r is 0, you can see here k is 0. So what we have done, you have created c00, and you have assigned your first bit, that is your b0. Second thing we will do, you will increment I and k both by 1. Now your I becomes 1, k also becomes 1. So you will do C01 and you will assign B1. And this process you will repeat how many times? Until k dash minus L minus 1. So you will repeat unless you have reached this number k dash, that is the number of bits should be there in each code block. And then we have to add L parity bits. So we are stopping just L bits before, so that we can add L parity bits and it will be exactly k dash number of bits. So that is the first thing we do. Then we check whether number of code block is 1 or higher. If the number of code block is 1, that is the first case, like trivial case, when your number of bits are less than the total code block size, the maximum code block size. So you no need to do any segmentation. That is the case. In this case, what you do, if the answer of yes, you simply add filler bits that I was talking about just now. So you add some filler bits and you are done. But if you have more than one code word, in that case, what you have to do, you have to again calculate this 24-bit CRC. The difference with this 24-bit CRC and that is that this polynomial is different compared to that. This polynomial is it's not same exactly. So if you go and read the standard, they have defined 24A and 24B. So basically this polynomial is 24B. Now you have calculated 24 bits, those parity bits, and then what you will do, you will pad those CRK, like all those K dash bits, K dash minus L2, K dash minus 1. So those K, like those L bits, you will pad at this parity bits. Once you have added this, so you are done with that particular code block. And if there are anything empty, like your K and K dash, K was 22 times ZC and K dash was the number. So if there is any gap, you will add again filler bits and you will repeat this process for next value of R, that is next code block, R equals to 1. So you will increment R to 1, you will repeat this entire process and you will repeat this process up to code block, like number of up to code block numbers. So that number was capital C. So you're starting from 0. So you should go up to capital C minus 1, that much. So this, by doing this, what happens? We have done, like break all the things, like say, transport block CRC into multiple code block. The next thing we will do up now is channel coding. So here you can see, if you pay attention to this figure, at this level, we have done code block segmentation. And because of this, you have CR0 to CR KR minus 1. So R stands for different code words. And here you can see there are multiple parallel boxes. So each code block, you will do a channel coding. So here there was only single box, the first 2, 3. Fourth block, there are multiple blocks because now you have multiple code blocks. And for each code block, we have to perform channel coding. So this part will be slightly involved. So I will be try to be as slow as possible so that you can comprehend the idea. So channel coding, we use low density parity check code. For channel coding, Ldpc code, that is low density parity check codes are used. It is, you can see at an extension of linear block codes. Linear block codes are part of error control coding theory. If you have read like any basic code, you will see that linear block codes are frequently used, and Ldpc is is an extension of that linear block code, where k bits in a code block are encoded to n bit message. So you have total k bit message that will be encoded to capital N bit message. And the purpose of doing channel coding is that error correction. So you should pay attention that CRC we have added for detection, whether some error happened or not. Ldpc we are doing for error correction. So you no need to do retransmission. So you can correct the error. So let me start with a review of linear block code. So I have considered a very simple linear block code, that is a Hamming code of 7, 4, and which have a following parity check matrix. So I have considered this parity check matrix. So you can see here, this is a systematic parity check. Here, this structure is identity, and you have these are your the message bit part. So for a valid code word, C, which has message bits are in one side and parity bits are on other side. So if you take H times C transpose, it should be 0. You should get a 0. Then only the code word will be valid. If it is not a valid code word, so what you will get some number here, 001, 110, something like that. And that will tell you which index, which place there is an error. So the number corresponds to which place there is an error. So here we are not talking about the detection part. It's like the receiver part. We are primarily concerned from the transmitter side. So I will just talk about how you will find this value of P. Like whenever you have some message, how you will find this P. So, and then you will form a code word and then you will transmit. So M can be a K bit message, and C will be a capital N bit message. So here you can see that M is your message bit, P is the parity bit, C is the coded bits. So so we can calculate, we can write like H C transpose H H1 H2. So you can see like this is the same matrix. We have just writing that entire thing into two parts. The first part as H1, which is a 4x4 matrix, 3x4 matrix, and the second part is your 3x3 identity matrix H2. And then C as M P transpose. There should not be this transpose here. This is a typo. So once you will multiply this H1 M transpose plus you will get H2 P transpose equals to 0. Now these are all like binary operations, like GF2, Gaussian fill 2 operations. So what you can write, you can always write this as like you can move this to another side, and since there is no like it will become H1 M transpose equals to H2 P transpose. So using that, what I'm writing H2 P transpose as H1 M transpose, and this P transpose, this H2, if I take this side, it will become H2 inverse H1 M transpose, and H2 is identity matrix. If you see here, this H2 is an identity matrix. So inverse of identity matrix will be again an identity matrix, and you multiply with any other thing, you will get the same matrix. So we simply remove H2 inverse from here, and we are writing H1 M transpose. So if you do H1 times M transpose, any 4-bit message, if you multiply by H1 times this, you will get all 3 parity bits, and you will pad it to your message bits to make a code word. So this is the overall idea of Hamming code. The same thing has been extended for Ldpc. So Ldpc retain the structure of linear block code. So it also has a parity check matrix. The difference is the size of parity check matrix and the density of ones and zeros. So usually for Ldpc, the parity check matrix is very big size. You will see how big it is. I will come to that. And it will have very few ones. Like if you have, let's say it's 100 cross, let's say 100 matrix, it may have maybe only how many entries? 10,000 entries are there. So potential out of 10,000, maybe only 100 entries are 1, or maybe 1,000 entries are 1. So it has very few ones, and most of the entries are 0. So so in 5G, like so your input bits code block size is either 22 times ZC. Again, I have not covered what is ZC. I will come to that. But for now, you say that, assume that ZC is a number. Okay, the maximum value of ZC can be, I think, 384, and the minimum value is 2. So it can be anything between 2 to 384. So 22 times some constant, for now you assume, for if you are choosing base graph 1, and 10 times ZC if you are choosing base graph 2, then, so this is your k-bit message. We perform an Ldpc coding, it becomes an n-bit message. And this n is something 66 times ZC or 50 times ZC. Right. So it becomes, so you can see here. So basically you are, if you see the k by n, so for the base graph 1, you will get 1 by 3, 22 upon 66. ZC will be same. And the second case, it will be 1 by 5, that is 10 by 50. It will become 1 by 5. So 1 by 3 in first case, 1 by 5 in second case. So every one message bit, you are adding 4 parity bits in second case, base graph 2. In first case, every one message bits, you are adding 2 parity bits. So this is that. And ZC represents an expansion factor. Encoding procedure, let me talk about how we encode, like how this 22-bit 22 times ZC becomes 66 ZC. So there is a lifting size index. This is an index which is conveyed by higher layers. So first, based on the higher layers, there is a table, and we compute the value of ZC. ZC such that it should be KB times ZC should be greater than K dash. So I will explain this. First, ZC is the expansion factor, and which is given by this table. So these numbers 0 to 7, you can see that these numbers are conveyed by higher layer. So let's say higher layer has conveyed this ILS value as 1. So what you will do, you will check like these are the possible values for ZC. So ZC can be 3, 6, or 384. And if you pay attention, there is a pattern here that I have written in at the top. ZC here is, it's 8 times of 2 raised to the power L. So first value is 3, second value is 3 into 2, third value is 3 into 2 raised to the power 2, 4, that is 4 into 3, 12. Third value is 3 into 2 raised to the power 3, which is 8. So 8 into 3 will be 24. 3 into 2 raised to the power 4. So everywhere you can see that pattern is there. So there is a base number 2, 3, 5, 7, 9, 11, 13, 15. And then you just multiply by 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2 with that number, and you will get this set. And how many numbers should be there? There will be maximum 7 numbers if you are picking these 2, 6 numbers if you are going with this index. And this table is defined by standard. Okay, now, so you can get the value of ZC. Now you know that this is the set. Let's say you have ZC as 1. So you know that the set will be, the numbers of ZC, possible ZC are 3 to 384 in this case. So what the next thing you will do, you will check KB times ZC, whether it's a greater than K dash. K dash, do you remember what was the K dash? K dash was the number of bits in each code block. Number of bits in each code block. So you will just do KB times ZC, and KB is defined by standards. KB is a constant. It is, the value is 22 if it is base graph 1. If the value is 10 if it is base graph 2, for the value is greater than 640. So B is your number of transport block size after CRC. The value of this B will be 9 if the number is greater than 560. If it is greater than 192, the number will be 8. 6 if it is less than 192. So you can see there are different regions. So it can be 22, 10, depending upon that. What you will do, 22, if it's, let's say its value is 22. So you will do 22 times ZC, and you will choose all these ZC, and you will see for which ZC, minimum value of ZC for which it is greater than K dash. K dash was the number of bits in a code block. Once you have determined that value, you determine your ZC. So ZC, the first thing that we have to find which ZC we should use. Fine. Let's move ahead. So the step 2, you will start assigning the message bits. So it Ldpc also, like the 5G Ldpc also has a systematic structure. So initial bits in the code word, initial part will be message, and the remaining part will be your parity bits. So what we do, we initially assign the message bits. So how many message bits should go there? So we set the value of k. These are the input. We just check whether ck is null or not. Null means whether it was a filler bits or it is not a filler bits. If it is a filler bit, then you simply assign dk minus 2zc as ck. So you will start assigning those values directly to ck. If it is not a filler bit, you will assign ck to 0 and this dk values as null. So basically, if it is, so you will assign all these values to that. If it is not a null value, you will simply assign. So you should pay attention to this case. So what you have done, k, if you put k value 0, so k here is starting from 2zc actually. So 2zc plus 1, 2zc plus 2. So d0, d1 will be c0, c1, and likewise the way we are assigning the value. Then we increment this value of k in both the cases and repeat the entire process. So we repeat the entire process. Whether you are at this or this, you will set the value of k to 0, assign that particular bit to the code word, that is your coded bits, and then you will repeat this process up to capital K minus 1. So capital K minus 1 was the maximum number of bits in your message. Like your message bit was K cross 1, capital K cross 1. So that many times you have to just check whether it's a filler bits or whether it's an actual message, and you will keep on assigning all the values. So this is the first part, but this part is very trivial. It's basically what you are doing in your code word, which is coded word is C here. So you just pick C from here. This is your code block message, and you have to calculate now parity. So you have simply fill all these values to D. The second part is the parity that you have to calculate. So how you will calculate the parity bit? So parity bits are, so total n plus 2zc minus k parity bits will be there. N is basically your 66 times zc or 10 times zc. Then you will add plus 2zc and minus k. K already you have filled. So that many parity bits you don't need. You already have message bits. So you add that many parity bits, and the base graph is having this size. So now we have talked about the base graph, but base graph means it basically base matrix. Although standard says it's a base graph, but it is actually a base matrix. And but this base matrix has many permutation combination. Here I am just writing the dimension. So it will be 46 cross 68 is the dimension if you are choosing base graph 1. If you are choosing base graph 2, the dimension is 42 cross 52. So these are the two dimensions of both the base graph. And what you do, you simply multiply H times D transpose, where D is your CP, and you can get your parity bits, and you can append those parity bits, and you will do the encoding done. Now, but we need to understand what is this H and how we can generate, it is called as a base graph. So I will just first taken some points from the standard, and then I will explain what it means. So there are tables. I think these tables are in 38.212, the standard number. So the elements in H, like what should be the value at row and column, it is determined by these two tables. First table is for base graph 1, that is 5.3.2.2, and the second table is for base graph 2. If you search these standards, you will find the tables. So this defines, so there are some certain rows and columns are given, like those values, the values which are given in the table, you have to fill those entries as 1, those elements which are not given in the table is filled as 0. Okay, so this that is the first thing you have to do. So let me just show you that table. So this is the table. Like here you can see there are row index, column index, and there are, let's say you have chosen ILS value as 1, and row index is 0 and column index is 0. So what you have to see here, the value should be 307. So in that edge, basically this value will be 307. I'm just writing 307, but actually this is a 1 here. What is that 307? I will come. But here you see that all numbers are not there. There are many numbers. If you see this 15, only row 1, row 10, row 13, sorry, 15th row, only column 1, 10, 13, 18, 25, 37 are there. What about the other row? You have to simply write 0 at those locations. That is the idea. That is the first point in this. The second point says that, so whatever the number you are seeing, that 300 or 200, you have to create an identity matrix of that structure. Okay, ZC cross ZC matrix. And so if the value is 0, it will be replaced by ZC cross ZC identity matrix, whatever ZC will be. If the value is 1, what you have to do, that you have to rotate, like identity matrix, you have to calculate this Pij, which is the mod of that 307, whatever that value is there, comma ZC. You have to take the mod, you will get this Pij, and you have to generate an identity matrix of size that, so let's say 1, 0, 1, whatever identity matrix you are getting, you have to cyclically rotate in that many number of times. So that is the key idea. I will again consider a small example so that you can understand this encoding process. So I have considered an example where ZC value is chosen to be 5. So this ZC is 5, and I have just considered a hypothetical table, which looks very similar to that table. So here you can see I have defined row index as 0, column index as 0, and this value is 1, right? Now, if you see the second row, I have defined row index 0 and 1, but there is a no value. Basically, that value is missing in the table. That value corresponding to row index 0 and column index 1. So this value is 0. What we will do is at this place, we will fill 0 matrix of size 5 cross 5. Then at the second, you will have this value 3, 1, 2, 5, and so on. Like these values, these tables you can see. So what you have to do, you have to take these numbers, Vij, you have to take mod of this number 1, 5. What would be the module, like mod of this? So basically, you are taking mod 5 of 1. You will get 1. If the value is 5, you will get 0. So at this location, if you take this mod 5, 5, you will get 0. So what you have to create a matrix. So this matrix you can see here. What I have written, I of 1. Simply I have written I of 1. Second element, like 0th row, first column, you can see I have written 0. 0th row, second column is your this one, I3. I3, this value is 3. And 3, again you are taking mod of 3, 5. So 3 will be 3. So if the value is less than 5, this value will be directly mod 3, 5 will be 3 only. Then we have filled all the values 1, 2, and these values were not present, so these values were 0. Similarly, if you see the second column, that is column index, row index 1 and column index 2, your value is 2 here. Now you notice this one, 5. So 5, 5, you will get I of 0, right? I of 0 means you do not need to permute I. It is simply I. 0 times. You are cyclically rotating 0 times. So I of 1, basically what you are doing, you have a, let me erase everything here. So these matrices, like wherever the value is 5, so mod 5, 5 will be 0. So So your rotation, there won't be any rotation in the identity matrix. So it is just I. So multiple places you can see that there is only I. Other places it is either 0 or I1. So 0. So now this entire thing, you can see that it is not only 4 cross 1, 2, 3, 4, 5, 6, 7, 8. It is not only 4 cross 8 matrix. Basically, each number here is a 5 cross 5 matrix. So what would be the size? So it will become 4 cross 5, that is 20 rows, and 8 cross 5, it will be a 40 column. So if you see the bigger picture, it will be a 40 cross 8, 20 cross 40 matrix. Okay, and it is a concisely written like this, 4 cross 8 form. And wherever it is I1, you have to generate of identity matrix of 5 cross 5, and you have to cyclically rotate it. So your fifth column will become first column will become second column, second, third will go to fourth, and fourth will go to 5. So something like that. Similarly, I3 means you have to cyclically rotate by 3 times. I1 means cyclically rotate by 1 times. I2 means cyclically rotate by 2 times. I4 means cyclically rotate by 4 times. So you will get a big matrix having ones and 0. And in this matrix, if I ask you how many total entries are there, if in this matrix also, there are 40 into, like, if you see, it is 20 into 40 matrix, right? So which is 800 elements are there, 800 entries are there. But how many ones are there? So you simply count I. How many I's are there? 1, 2, 3, 1, 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, then 16, 17, 18, 19, 20, 21. Only 21 I's are there, and each I is an identity matrix. No matter whether you do a circular shift or whatever, number of ones will be 5 only. So 21 means 105. So only 105 ones are there out of this 800 entries. So you can see that it has a very low density. That's why the name comes low density, and it has the same structure that parity check matrix is there. Slightly different structure. If you see this part, this is not exactly identity. Like in the parity check matrix, this part was exactly identity, and it has double diagonal structure. Like if you see this will have identity at its diagonal, 2, 1, 1, 1. So it's not a single one, it has 2 ones at the diagonal. And that also has a reason, that is to make it more convenient decoding at the receiver. So if I just draw it, you will see like something like this. So your base graph 1, if you remember, it was 46 cross 68 channel matrix, and this was, if I'm not wrong, this was 52. Let me see. Yeah, this was 42 cross 52 channel matrix. So this, if you see, this entire thing is divided into now 6 regions. So I will talk about, let's say, one base graph. The same thing is applicable to base graph 2. So in this, you can see that this region, all these greens are basically are your ones. Wherever you are seeing 1, green dots, they are 1. And all empty places are zeros. So you can see here, this part is highly dense. Like this has a significant number of ones and ones. But this part, excluding this first 2 lines, like this part, mostly it is also quite empty. But if you see that this part and this part, this part is like almost, this is basically identity only. And this part having that double diagonal structure, like it has 2 diagonals of ones. So it has this kind of a structure of Ldpc encoding, and it helps us to like why this structure has been chosen. First thing is that like it makes the decoding easy, and it is very easier to protect the messages. So these are the primarily 2 reasons for which we have considered Ldpc encoding. So this is the entire process. Now, how we do 2-step. So it's basically encoding is a 2-step process. Once you have channel matrix, what you do, So what we can write this as code word the message as M, P1 and P2. P1 is the parity bits coming from that double diagonal where we have two diagonals of ones. P2 is coming from the identity part, and you have a message bit. So H, M, P1, P2 transpose, and H is this, your A, B, C, D, and T, E. B is your double diagonal structure. E is basically your identity matrix. T was everything was 0 in T. A, C, and D was that the other parts of that base graph. And what you do, you implement this expression. So if you implement this, you will get your P1, that is your parity 1, the first parity bits, and this P2 is your second parity bits. So applying this, you will get both the parities, P1 and P2. Now moving to the last step. So since you have now computed the parity bits, what we have to do, you have to do the assignment. So this part, step 4, you are assigning the parity bits to your message, the code block, that is D0. So this D0 to D2ZC, this DN is your coded sequence. The next module, we do a rate matching, because if you remember, rate matching, if you see there are two graphs, base graph 1 and 2, one having 1/3 rate, one was having 1/5 rate. But actual, you may not need that much of rate. You may be able, your desired rate is maybe 1/2. You want 2/3. How you can generate those kinds of rates? So the idea is that you want to generate any arbitrary k/n. So if you go with that logic, like 22ZC or this logic, you will always have 1/3 base graph 1, 1/5 for base graph 2. So what we do to match the rate, we remove some bits, we discard some bits from here. Like whatever 66ZC, if you, let's say, if you discard 22ZC from here, let's say you discard in the base graph, you discard the parity bits, last 22ZC parity bits. So how many bits will be there? 44ZC. So what it will become, 22 divided by 44, it will be rate half. So you have to discard something so that you can match the rate. 1/3 and 1/5 is like one extreme, and you can have 1/2, 2/3, or all such possible combinations are feasible. So desired rate, code rate is achieved by using a bit selection method. So we have to select some bits and we have to discard few bits. So that by doing that, we can do the rate matching. This block has an additional purpose. It also do a bit interleaving. And this is done for protecting the transmit data against the burst error, burst noises. So in the communication system, what happens sometimes, suddenly your channel goes into deep fade and you are not able to receive anything meaningful for some period of time. So what we do, we interleave the data so that whatever your errors, burst errors, that will be spreaded across the code block, and your Ldpc encoder or decoder, it will be able to decode that particular message. So that is the idea. So these two things is done in this at this block number 5. So we'll talk about bit selection first, how we do that. So consider ER is the rate matching output sequence. So ER is the number of bits you want, like instead of n, you have n bits after n bit in Ldpc encoding, but you only want to transmit ER. So you have to discard something. So how you'll find what should be the value of ER? So the value of ER is determined by this expression. So if an R is for the code block, RS coded block. So if you are talking about 0th coded block, first coded block, every code block you have to calculate this number. So first you will check whether that particular code block is scheduled for transmission or not. This scheduling is done by higher layer, whether it is scheduled or not. If it is not scheduled, then you won't transmit anything. In that case, that ER will become 0. So basically out of n, you are not transmitting any bits. If it is scheduled, then you have to check for these two cases. So here, let me first introduce what are these notations. Your G is the number of coded bits available for transmission. So how many coded bits are available for transmission? So let me erase everything. So let's consider G is 1004. Okay, these are the bits, let's say, we are available for transmission. The second thing is that your number of layer. So let's say NL is 2. So number of layer we have not covered. You can consider that it is a like how many parallel transmissions you can do. So let's say this value is 2. QM is the modulation order. Let's say this value is also, you are using QPSK, this value is also 2. Okay, and C dash is the number of scheduled code blocks, and J is a running index. We will come to what is this running index. So first you just check, this is 1004 divided by, and C, let's say this value is 4. So what will happen? C dash is 4. So your total value is 1004. And if you see this inner term, just focus on this inner term. They are same. Only one place you are doing seal operation, one place you are doing float operation. So 1004 divided by 2 into 2 into, let's say 4. So what is the value you will get? The value you will get 2 into 2 into 4, that is 64, right? Sorry, not 16. 1004 divided by 16. So what is the value you will get? So you will get something like every, you have 4 code blocks. So each code block, like you are doing 4 code blocks. So each code block should have 250, 250, 250, 250, and one code block should have 254, something like that. Or okay, let's consider 2001. So what will happen? Every 3 code blocks should have 250, 250, 250. One code block should have 251 bits. That is the idea. This expression is doing that. So that's why the seal and float operations are there. Otherwise, they are same. So what you can understand that you are finding how many number of ER, like this rate matching should be there. So it depends on this expression, and you will able to know what is the number of lengths. So maybe 1001. So what will happen? You will get 250 in the first 3 and 251 maybe in the 4th one. So here that is decided based on a running index J. So it is initialized with 0. So first it will be 0, and with every code block it will be increment to 1. So that if anything is left over, so it will first go to the float operation. If anything is left over, it will take the seal operation, and that extra bit will be added to the later code words. So initial code words will have float, later code words may have a seal of that value. So you know that how many number of bits you want to transmit, but how you will do? So actually there are 2 methods, puncturing and shortening. So puncturing, there are 2 kinds of puncturing. One is message bit puncturing. So these 2 bits, first 2 bits, 2 ZC bits actually, not 2. First 2 ZC, 2 columns, 2 ZC bits are always punctured. So this is your message bit puncturing. We call message bit puncturing. So if you see here, it is 22 and 46. So what should be the length? 22 plus 46, it should become 68, right? But your message was 766 times ZC. This is because these 2 bits are always punctured. Same if you see the first one, it is 10 plus 42. So it should become 52. But if you see the number of N, it is 50 times ZC. So these 2 message bits are always punctured. Now, second puncturing is that parity bit puncturing. So what we do from the back, we will puncture some bits. So like if you want to rate half, what you will do, you will puncture 22 times ZC number of columns from this side. So that is your puncturing, parity bit puncturing. Second thing is that sometimes it's possible that you have to do further shortening of message bits. So in that case, what you do, this block, this portion, you will start shortening, you will reduce message bits. So you will, once you will reduce the message bits, so that we call as a message bit shortening. So there are two kinds of things, puncturing and shortening. We use them for removing the some bits so that we can match the ratio of k by n. So whatever n, we are changing it to some capital E, so that your rate from k by n, it will become k by E. That's it. Now interleaving is a process which is done after this. So you have now E0 to E capital E minus 1. This is your after puncturing or shortening. These are the bits you have available for transmission. So what we do, we use this expression. So I will explain what is this expression to do the interleaving. So where like capital E is the total number of coded block bits available for after bit selection. QM is your modulation order. I varies from 0 to QM minus 1. And J varies from this number. So I will explain how it is happening. So let me move next. So let's say these are your all E0 to E capital E minus 1. And what we have done, I have just divided into separate colors. E0 to E by capital EQM minus 1. Then we have E capital E upon QM to E 2 times of E by 2 QM minus 1. So you can see these colors. What we do, we simply arrange all these numbers in a matrix. So like something like this. We first write E0 here, then E1 here, this like this. So we assign all these numbers in this order. First this, then this, and then we read in this order for interleaving. So first we read this, like this, like this. So after interleaving, this will become something like this. So E0 will come here. This green portion will come here. This blue portion will come here. And we will transmit this packet. So this is like we have jumbled up the bits in a particular fashion. And that fashion depends on your modulation order and the value of capital E. That's it. So these are the two things, rate matching block we do. So as a summary, we have n bit message, encoded message. We perform bit selection. This n becomes capital E, where capital E is expected to be less than capital N. And then we perform interleaving. This sequence of E0 to E capital E becomes F0 to F. So this E0 may be F0, E1 maybe goes to somewhere here, and likewise. So this was the rate matching. The next module is code block concatenation. So what we do now, we have performed all code blocks, everything, all code blocks, we have done the same thing. So you have multiple code blocks here, right? Now at this, what we do, we concatenate them. All the bits from different code words are arranged in a sequence, something like this. So you have this is your first code word, let's say code block. Let me write, this is a CB0, this may be your CB1, this may be your CB2, code block 2, and this may be your CB, let's say capital C minus 1. Sorry, capital C minus 1. So what we do, we simply put this CB0 first, all the bits, then we put all CB1 here, then we have all CB2 here, bits of, then we have CBC, C minus 1. So now this all code blocks we have again arranged in a same one sequence. So earlier also we started with one sequence and we end up with one sequence, which is G0 to G minus 1. So this is the entire flow of transport channel processing. Okay, so it started with CRC attachment, base graph selection, segmentation, then we perform Ldpc channel coding. The rate might be very low, 1/3 or 1/5, so that we match it to our desired rate, maybe half, 2/3, any rate. Remove some, we have ignored few bits, like either through puncturing or shortening, and then we perform interleaving, and then we arrange all these bits in a sequence. The first code block will be your first few bits, then second code block will be your second few bits, and likewise. So this is all about transport channel processing. Now we will move to the physical channel processing, and we will start with the first block of physical channel processing, that is scrambling. In scrambling, the idea is that it is used for the following purposes. The first purpose is that it is it is used for protecting from any unauthorized access. So what happens? We are transmitting bits, and those bits are from different users. So we do not want user 1 to decode users 2 data or users 2's data to users 1 data. So if we, in the bit sequence, we multiply by some another code, so that without that code, the other user may not be able to decode the data. So that is the first purpose. So it is protecting from any unauthorized access. Second is that your bit sequence may not be properly randomized. Randomized means that entire packet, your mutual information can be maximized if the bits are equally likely. It means there are equal amount of 0 and equal amount of 1. So this scrambling sequence helps us to achieve that. Further, it helps to reduce the interference. So what happens, it is likely that there is two sequences or two same message data are very correlated. Like they might have, let's say you have a 100-bit packet, and user 1 and user 2, maybe 80 bits are matching or 60-70 bits are matching. So what will happen? Their signal will interfere in a good amount. But if once you have done the randomization of bits, that bit pattern will be very different. And because of that, the amount of interference that user 2 is causing to user 1 or vice versa, that will reduce. So that is the third purpose. Fourth purpose is that maintaining the synchronization. What happens? Let's say you have a long sequence of zeros. So what will happen? Your receiver may get out of sync. But if you have very alternating sequence, so every alternate, your receiver can keep the track of the synchronization. It will not lose the synchronization. So that is the one purpose of doing this scrambling. And scrambling is also done to support multiple transport blocks. Whatever chain we are studying in 5G, there could be 2 parallel chain can go together. So one chain for one code word, another chain for another transport block. So there are 2 code words, and both code words will have 2 separate chains. So that is so the data from on both the chains can be distinguished from this scrambling. Then we have a procedure. So what is the procedure of scrambling? So we have a coded bit sequence. Here you can see that BQI. This is the coded bit sequence. So it can be any bit, 10, 11, whatever. A Q represents which code word you are talking about, which chain you are. So the Q value can be 0 or 1. So because there could be maximum 2 code words. So that's why this Q comes into the picture. We do an bit level scrambling with some sequence called CQI. So we generate another bit sequence, that is B tilde Q, by taking an XOR. So we sum these two and take the mod BQI and CQI. BQI is your actual these bits before scrambling. CQI is your scrambling sequence. You do an XOR and you get your B tilde Q. Now this CQI is generated using XOR of 2 gold sequences, which is given by this. Ci this should be Cn. Okay, Cn could be x1n plus 1600 plus XOR with x2n plus 1600. So mod 2 is basically doing you can simply say that it's an XOR of these 2 sequences. Now what is x1n? X1n is defined something like this. So it's like if you know few sequences, you will be able to generate the entire sequence. So it has a recursive relation. So x1 n plus 31. So 31 n plus 31 bit depends on n plus 3 bit and nth bit, and you have to do an XOR of these 2 bits. Similarly, x2n plus 31 depends on x2n plus 3, x2n plus 2, x2n plus 1, x2n plus sign is missing here. So plus of all these XOR operations. Now you may be wondering, all this sequence, if you want to generate, you need some initialization. So for generating all the sequences, we need first 31 values. Then only you can generate x1n plus 31 or x1, x2n plus 31. So what is the way? So the standard x1n, the standard fixes the initial values. So x1 0 is 1 and x1 1, x1 2, x1 30. So is 0. So the first sequence x1 0, like you can say like this value is 1, and other values, all 30 values are 0. And once you plug that, you will start getting entire x1n for any sequence. Whereas the initialization of second sequence, that is x2n, depends on a decimal number, basically a binary equivalent of a decimal number. So there is a number called C init. This C init you have to calculate, and this will be a decimal number. What we have to do, we have to convert it to binary number, and the LSB of this number will be your x20, and MSB of this number will be your x230. And the relation given here is, this depends on a radio network temporary identifier, that is eta RNTI. This value ranges from 0 to 65,519. It can be any value in this range. Q is your code word. So Q here is your code word, which can be 0 or 1. Eta ID is a number from 0 to 1023, and this eta RNTI is 0 to 65,590. So after doing all these things, what we will get? We will get a 31-bit number, and that 31-bit number will be used for generating the second sequence. So by this, we will be able to complete the scrambling. The third block in this, the next block in this is the modulation. Modulation, it is a process to convert a binary sequence to a complex number sequence. So there are 4 schemes are allowed for downlink. So 4 modulations are allowed. This is the table. So first is QPSK, where 2 bits are mapped to 1 complex symbol. 16QAM, where 4 bits are mapped to 1 complex symbol. Then 64QAM, where 6 bits are mapped to 1 complex symbol. And then we have 256QAM, where 8 bits are mapped to a 1 complex symbol. So let me explain about the QPSK. So QPSK, there are 2 pairs of bits, B2I and 2I plus 1, where I you can change from 0 to 1, 0 to, so if you put I0, you will get B0, B1. If you put I2, you will get B2 and B2 into 1 plus 3, that is B3. And likewise, so what we will do, we will pick 2 bits and we will map to a complex symbol. And that expression is given by something like this: 1 by root 2, 1 minus 2b times 2i plus j, 1 minus 2b, 2i plus 1. Now, this standard specifies this relation. So you cannot choose any other mapping. You have to choose this mapping only. So this leads to following 4 possibilities. So like you have 2 bits, so you can have 0, 0, 0, 1, 1, 0, 1, 1. If you plug 0, 0, what you will get? 1 plus j. If you plug 1, let's say 1, 0, what will happen? 1 minus 2 into 1, that is minus. So you will have minus sign plus j. So wherever 1 is there, there will be minus sign. If there is a 0, it will become a plus sign. And 1 by root 2 is your 0.7071. So you will have these 4 constellations. So if you map these to constellation, you will get these 4 points. And you have to, like, this will be your 0, 0. This will be your 1 minus j. This will be your 0, 1. This will be your 1, 0. This will be your 1, 1. and you have to use this only. You can't use some other pattern. So this is about QPSK. Similar tables are given in the standard. If you want, you can read that particular section. So just to highlight. So here, if you see all these blocks, it is also specify which sections you have to read. Like modulation, you have to read 38.211. Section number is 7.3.1.2. So if you read there, you will get all these QPSK, 16 com, all the expressions for all the 4 modulation. By doing the same thing, you can able to generate the constellation for all even 256 com, 16 com, 64 com, all others. Here, let me ask you one question. How modulation scheme, like how a base station will decide which modulation schemes to choose or which modulation scheme to transmit. So the idea here is that if you go higher in the modulation order, let's say you are going from 2, 4, 6, 8. If you go higher, your data rate will increase, but your error probability will also increase, right? So QPSK will have best error probability, like lowest error probability, but it will have lowest error rate also. So we want our system to work somewhere at the highest data rate and lowest error rate. So how we can do that? So for this, standard adopts like measures the channel quality. What is the channel quality? What is the channel scenario? And based on that, if channel quality is good, it will take it will transmit at the higher modulation scheme. If channel quality is bad, it transmits to a lower modulation order. So it basically depends on a 5-bit CQI value, that is a channel quality indicator. This CQI value is conveyed by the user to the base station. Based on this, it basically conveys the channel quality. Higher the CQI, if the CQI value is higher, so 5-bit value, so what will be the maximum value? 31. Lowest value will be 0 because it's a 5-bit number. So if you are seeing, let's say 28, 29, 30 or some higher values, you will use 256 com, or base station will use 256 com. If you are seeing a lower value, you will use a lower constellations like QPSK or 16 com. And there is a table here which is defined by the standard, and this basically has a MCS index. This CQI number will come here. A vendor or a manufacturer will make this mapping depending upon their requirement, and they can use that particular modulation order. I don't know whether you can see this table or not. It slightly looks small. And here you can see the code rate. Whatever you're picking, your code rate will be also based on that. It will be predefined. Okay, now I'm moving to the next block, which is layer mapping. Layer mapping is equivalent to spatial multiplexing in multiple antenna system. So basically what we are doing, we are transmitting parallel streams of data. So and in 5G, there are maximum in downlink direction, there are 8 parallel streams are supported. So you can transmit at max 8 parallel streams in downlink direction. In uplink, this number is 4 only. So here there is a table in the standard. So I will explain this. So if you have let's say layer mapping, like you have 2 layers, what you do, you take the first symbol and you will map it to the layer 0. Immediate next symbol will go to the layer 1. Then again, so what essentially means, if you have, let's say D0, D1, D2, D3 and so on. So what you will do, all even number will go to layer 0 and all odd number bits will go to layer 1. So you will basically, you are creating a 2 parallel streams of data after layer mapping. Then if it is a 4 layers, then what you will do, if you have, let's say D0, D1, D2, D3, D4, D5, D6, D7. So what you will do, D0 will go to the first layer, D1 will go to the second layer, D2 will go to third layer, D3 will go to fourth layer, then D4 will go to first layer, D5, D6 and D7 and so on, like D. So you have every like alternate fourth bits like D0, D4, D8, D12 will go to first layer. D1, D5, D9, D13 will go to second layer, and so on. Similarly, this is the case I have picked where you have two code words. When you have two code words, so it's basically you have to see this number. In this case, what we do, the first code word will map to first 4 layers. And the second code word will map to the second 4 layer. And this mapping will be same as whatever we have seen just now, that is one code word with 4 layers. So you have two code word and 4 layers. So you will have two code word 8 layer. So what you will do first, you will map one code word to the 4 layer and second code word to the second 4 layer. So this mapping will be also same, like you will pick first data, map it to the first layer. You will pick the next, like skip the third symbol, 3 symbols, and then you will again go to the fourth symbol. You will map to the layer 1. And likewise. So you will do that way. So that this is your layer mapping. So the idea is that you have a bit like complex symbols. You are making it to parallel like stream of data. Then we are moving to the next block, which is antenna port mapping. Antenna port mapping, do not get confused that we are mapping into a physical antenna. Antenna ports is just a logical concept in 5G. It is not a physical antenna. Physical antenna will come into the picture very late. Here, what the aim is to that is that if similar kind of data should have a similar antenna port, like if you remember, if you know like FTP, you have FTP is file transfer protocol, which has a computer you assign a port number 22. It is something similar to that. All layers of data, like if it is layer 0 data, it should have a fixed port number. If it is a layer 1 data, it should have a fixed port number. This is to make it convenient for the user side to know which which signals to look forward. Like one port of data belongs to one kind of signals. So if you see the standard, like for PDSCS, the antenna port number are defined from 1000 to 1011. So there could be 8 layer maximum. So this can be 1000 can be your layer 1, 1001 can be your layer 2, 1003 can be your defined for layer 3. So all layer 1. Apart from PDSCS, there are some pilot signals and reference signal also being transmitted. That is used for channel estimation and other purposes for data decoding. So if it is related to layer 0, that DMRS should also be assigned same port number, so that you will see that port number, and based on that you will do the channel estimation, and then you will do the data detection for the same data at the receiver side. So this is just a logical concept. It is nothing to do with anything physical. Like it is just an arrangement so that it is convenient to know which signal belongs to which antenna port. Like they belongs to same category. Like you have to first read this signal, then you have to read this signal, then you have to read this signal. Next block is relevant because that there we are actually mapping these signals to a virtual resource block. So every antenna port will have their own virtual resource block. So resource block is like it's like in 5G, it's a time frequency resource block. Like if you see this, it will have some time because it uses OFDM structure. It will have time and it will have frequency. And whatever our data, we will fill like layer 0 data will, like let's say some antenna port 0 data will fill here. So we will start filling that data into this grid. And this one cell here, like one cell of this grid called as a resource element, and that carries one complex symbol. So that carries one complex symbol or that modulated symbol, you can say. So what we do within resource grid, we fill resource element with PDSCS data. So we start from lowest carrier frequency. This is, let's say, this is frequency and this is your time. We start filling data from this end and we fill in upward direction and we reach to the highest carrier frequency. Then we jump to the next time instance. Again, we go back to the lowest part and we keep on continuing, repeat filling this data until we have exhausted filling all the data. And this is mapping we are doing to the virtual resource block. But here, one thing you should remember that this entire resource block may carry other signals also, because antenna port 0, it is not only for PDSCH. All the related signal which is required for this PDSCH data detection or decoding, that will be also there, like DMRS, which is your pilot signal, that probably will be at the second symbol, let's say this signal. So you have to skip while filling this data. You do not you should not write anything at this location because they are reserved for some other signal. So you have to skip that signal and you have to overwrite. So this is the overall flow in mapping to VRB. Now we are moving to the last block in this chain, which is virtual resource block to PRB mapping. So what we do, there are two types of mapping. So we have every antenna port, we have created a virtual resource block. Now we want to transmit. So we will transmit, every antenna will transmit a physical resource block. So this VRB, we need to map it to physical resource block. So there are two kinds of mapping, like directly we will map one antenna port to directly physical antenna, or it can be interleave, like multiple antenna ports are coming to one place. So there are direct and interleave mapping. Direct means there is no change. You simply, whatever your resource grid, your resource assignment is there, you map it to the physical resource block directly. And then you have interleave. Interleave means you have some information is going here, some information going somewhere else. So it will be an interleave kind of mapping, and it depends on various parameters. I'm not going to cover that part. So this is overall flow, like you have interleave mapping and you have a direct mapping. So you have a virtual resource block, you map it to the physical resource block. That's it. Now, once we have done everything, like we reached at this 12th place, what we have to do next? Now we have everything in the resource grid. Now we have to transmit OFDM. So once the information is mapped to PRB, we use cyclic prefix based OFDM to transmit the data. And what is OFDM involves? It involves three things. IFFT, because you already have a data in a grid form. What you will do, you will pick this first all subcarriers. You will do on some, let's say 4096.IFFT. This is the maximum size in the 5G that is allowed. So you will do 4096.IFFT and you will get an like after IFFT data. And then what you will do, you will convert that to a parallel to serial conversion, and you will add CP, cyclic prefix. You will add some cyclic prefix and you will transmit, and you will repeat the same thing for all symbols, all these vertical columns of this resource grid. So this is the overall understanding of downlink transmissions in 5G system. Now I will talk about I have used 5G toolbox to model all these blocks that we have studied so far. So this is the transmitter side. Here, if you see, like at least you can read the names. Like this is the first part where I'm generating the bit sequence, the random bit sequence I'm generating. The second part, once you have generated the bit sequence, which has a capital A length, what I'm doing, I'm adding CRC. So this is the block number 1. So this is your input data. This is the NRCRC encode. This is a function, like all these functions you can find in the 5G toolbox only, like this NRCRC encode. This function, what it does, it adds CRC. Whatever is that we have studied, that same thing it implements. Then we do a code block segmentation, that is second block. Then at the third, we do this Ldpc encoding. Then we have this output length. Sorry, so we calculate output length, what is the length we want, and based on that we do a rate matching, which is the basically this was the 5th block, and this 3rd and 4th is happening here itself. Then we have scrambling, which is your like concatenation is also happening. 5th and 6th is happening together in this rate match Ldpc. Then we have 7th block, which is scrambling. Then you can see there is a modulation and then layer mapping. So I have covered till layer mapping. Then we have antenna port mapping, which may be relevant only if you have very like actual system. And like in practice, you don't need that because this is just a plain one single channel. So there is no like multiple channel involved, so that you need some port number for that. And then after that, you have to map it to a resource grade. But since I have, what I have done, I have not used OFDM based transmission here. I have not used OFDM based transmission. I have simply used an AWGN channel. Okay, so what I'm doing, I'm simply transmitting 1 bit at a time. So this is the AWGN channel, which you can see here. I have generated a random noise, complex noise, change the power of the noise, that way basically standard deviation we are changing, so that variance will change, multiplying with the standard deviation, and then we are adding that noise to the transmit symbol, and we are getting our receive symbol. At the receiver, we have to use just reverse order. Whatever we are doing at the like we have to do everything in the reverse order. So we have to start from layer demapping first. We have to first demap the layer data. Then we have to demodulate. This is your demodulation function. Then we have to do a descrambling, which we are doing it here, this function. Then we are doing rate recovery. So rate matching we have done at the transmitter. Here we are doing rate recovery. Then we are doing Ldpc decoding, and then code block desegmentation. There we have done segmentation. Now we are doing desegmentation. So basically we are combining them, removing CRC and combining them, and then we are doing CRC decoding. And finally, we are getting our, after CRC decoding, we are getting our output data and transport block. If there is any error at the, like based on the CRC, this number will be 1 or 0. If it is 1, means there is an error. If it is 0, there is no error. And finally, we use some simulation parameter like capital A, we have taken 10,000 bits. Rate, we have considered 449 divided by 1024. And we are not using any retransmission, so we have considered this redundancy version at 0. We have not talked about also in this class, but once you will use the MATLAB functions, you have to pass some inputs, and this input was required, whether you want a retransmissions or not. For that, it is required. Modulation, we have used QPSK. Number of layers also we have used 1. SNR dB we set -2 to 2 dB, and there are some values which is used for generating the scrambling sequence. And this is only one Q. There are only one code word, and this is the bit error rate performance we are getting. So you can see here it is starting from like -2 dB. The bit error performance was too bad, but as we move from -2 to -1, it has significantly improved. And from -1 to -4, it has gone down to like 10 to the -1 to 10 to the -4. So you can see within 0.4 dB, we have improved a lot. And this, and there is a much like the entire thing, like basically it is Ldpc part is helping this, because anyway we are not using multiple layer, it's single layer. So why we are getting this steep down, that is primarily because of the Ldpc part. We are getting a very like -1 to -0.6, we have got a very good bit error rate. So let me summarize this talk. So in this talk, we understood the detailed procedure of downlink data transmission in 5G system. The procedure primarily categorized into 2 parts. One is transport channel processing, and the second is physical channel processing. The transport channel processing is responsible for error detection and correction part. That is, error detection is with the CRC and correction with the Ldpc part. And physical channel processing is responsible for actually MIMO OFDM kind of transmission. So we have a modulation, layer mapping, all those parts are here we are doing. And actually we are mapping into the physical resource block, and then we are transmitting based on the OFDM structure. So lastly, we used 5G toolbox to replicate the entire PDSCH chain. And we have concluded this talk. So in case you like you want to visit my website, I am available at this. My LinkedIn address is this. You can contact me on my email ID and my phone number, my office phone number. So with that, I am thanking you all and giving me the opportunity to present here. And any questions if you have, then you are welcome. Yeah. So is there any question? Yeah.
If anyone wants to ask questions, please ask.
ఎక్స్చేంజ్ చేద్దామంటే అది ఉంది కదా ఏ నెంబర్ తీసేసి ఇది పీడిఎఫ్ అది పీడిఎఫ్ కలిపి ఇది పీడిఎఫ్ చేసి అది పీడిఎఫ్ చేసి రెండు జాయిన్ చేద్దాం, అయిపోయింది. సింపుల్ పార్ట్.
Sir, thank you so much, sir.
Yeah.
It was very enlightening.
Yeah, thank you.
New insights into the domain of 5G technology. Surely our participants have learned valuable things, and after this FDP, definitely they will be able to explain and explore 5G concepts in a better way. Thank you very much, sir.
Yeah, thank you so much.
Thank you, sir. Thank you, sir.
So there is no question, right?
Yes, sir. No one is asking any question. Yes, sir. Thank you.
Okay, fine. Okay, so I'm leaving the meeting then.
Yes, sir. Yes, sir. Thank you, sir.
Yeah. Okay.
Yes, dear participants, now I will share attendance link in chat box. Please wait.
అక్కడ నా కాల్ ఉంది, ఇక్కడ కాల్ ఉంది మీకు. సరే సరే.
Chat box. Chat.
back button nokku.
sharp speed